Hi Rob, you there?
Yes,
Good.
I am, but I was just checking that everything was working because I have to wear headphones because it's late at night.
Yeah.
How are you?
I'm setting it on YouTube live, so I will post the link on YouTube. We can maybe for now wait with the
Yeah,
demo.
yeah. Look, I'm just testing it out. I'm about to go off and get a drink or something before the session.
Good.
Yeah. All right. Okay. Well, I'll see you in half an hour.
Yeah.
I'll
Thanks.
back in. All right. Cheers, mate. Bye.
Hello, everyone. How's it going? Can you hear me well?
Good.
Well, nice to see you.
Good, thanks. I was just testing Gatherly. I don't know if you tried, and it gives me the impression that we might stay with the breakout rooms in Zoom.
Oh, that's good. Okay, here comes my first speaker.
Hello.
Hi, Riyad.
How are you?
Good. How about yourself?
Well, we are losing the football match, so not great.
Yes, but you got to stop missing. That's all.
Yeah, they
Hey,
should
Ralph.
stop pulling at the thing. So,
How are you, Riyad?
ça va? How is the fishing, Ralph?
Very nice, thank you. Can't complain.
I can. You know, I was in Fire Island last week, and I went surf fishing. It's amazing how much hit I had, like this huge fish. The pro
Very good.
to take them out.
Very nice.
When
Oh, who's this?
are you returning?
Hello.
Oh, who's talking? I can't see. Hold on a second. Let me see if the other version.
Hello.
Hi.
Hey, I'm Sushan. Hi, Ralph. Hey,
Hello, how are you?
I'm good.
Sushan,
Hey,
good to see
Susun, how are you?
Yeah, how are you?
It's 10 p.m. at my side.
Yes, for me it's 6, so I'm a little bit earlier than you, I guess.
Hi, everybody.
Hi, Kia.
Hello.
How are you?
Great.
Good.
Melting. It's very hot today.
Oh no. It's been hot in Europe in general, hasn't it?
Yeah,
Not in
very
Sevilla.
humid.
In Sevilla, it's actually cool today and
Oh,
raining.
really? Oh, okay.
Yeah.
Interesting.
Hey,
Bernadette, your microphone is a bit low. Could you try to increase the volume?
Oh, 60.
Hi to everybody. Hi Guillermo.
Hi, Davide.
Hi, Davide.
Hi.
let's wait one more minute and then we start.
We are waiting for David and Costas also.
Yeah, David, I think he has another.
I'm here.
Ah, Costas. Okay.
Hi, Costa.
I think David is busy with another talk.
Good morning, everybody.
Hi, Costas.
Morning.
Morning.
Okay, let's go ahead and start because then we will run into troubles in time. Welcome everyone to the third international workshop on event-based vision. I'm very happy that we are all here and we're going to make the most out of this this time at CVPR 2021. So what you can see here on the slide is the link to the workshop website, and that's our main point of information. That's what this page looks like. And, on the webpage, we will find the schedule. It's very, very important. And we have videos, slides, papers, and very useful links. We are very happy that we have this great panel of speakers with us and that they make a huge effort to prepare the videos and make them available pre-recorded for us to watch in advance. If we haven't watched the videos, don't worry, because we will still do like each speaker will do like a summary presentation and then we'll have a panel discussion. So our sponsor is Prophecy. This workshop is sponsored by this event-based camera manufacturer, and we also have co-organizer Davide Migliori is also from Prophecy. Very happy that he's part of the organizing team. So we would like to thank you. We would like to thank the CVPR and the workshop chairs for allowing us to organize this workshop. Last time we had it at 2019. And now we are doing it again every 2 years. We thank a lot the invited speakers for preparing the talks, the summaries, and the pre-recorded videos. We also would like to thank the contributors of the submitted papers and the reviewers for helping with the fast and thorough review process. And I would also like to help the co-organizers of this workshop, Davide Scaramuzza, Kostas Danielidis, Cornelia Vermüller, and Davide Migliori. Okay, so the topics, I think we all know, that's why we are here, but basically we have the latest event-based cameras. We have big panel, well, great lineup of speakers in terms of companies. I think we are not missing anyone. We also have not only in event cameras, but also in neuromorphic hardware. We have the Intel Loihi, we have Julia representing that. And yeah, regarding the papers, we have 4 new data sets, 2 new simulators, 1 competition on depth estimation. And the papers cover a wide range of topics from optical flow, corner detection and tracking, image intensity reconstruction, feed map control, and many, many applications that we will see on the talks. So this is the summarized schedule. Basically, we are starting now. We have 3 minutes till this first session. There will be 4 speakers per session, and each one will give a summary of their talk, about 10 minutes. And we will have the questions at the end. We will have a panel discussion that should be 20 minutes long at the end of each session. The times that you see here on the slide are Eastern times. That's 10 a.m. on the East Coast. Here are the names of each person in the speaker in each session. And in the middle, we will have an intermission. We will provide the results of the competition, the award ceremony, and then we'll go into this poster session of the accepted papers and courtesy presentations. I was just checking the way how to do it. And I think we will all try to make use of the breakout rooms because I didn't see many people there in Galilee. And session 3 and 4 will be after this 90-minute intermission, and then the last panel discussion concludes the workshop. And this is the layout that I will put online when we come to the intermission. So here are all the accepted papers and also the courtesy presentations. And just to summarize a bit more, how the field is growing. I like to keep track of these statistics. This basically shows in the last 6 years how many papers are published at computer vision and robotics venues, right, that were not before. Classically, event-based vision papers have been published in other venues, such as the transactions on neural networks and learning systems. But this is basically showing a positive trend, a growing trend of many more people joining and researching on event-based vision. We have a list of event-based vision resources that we created a few years ago, and I encourage you to go online, check this list, and also add your papers and your videos, your data sets on this GitHub repository. It should be a joint effort, not just the effort of a couple of people. If you want to dive more into event-based vision, which I'm sure many people here already know, but from the first workshop it came out, we worked on a paper with transactions on pattern analysis and machine intelligence that finally was accepted last year. And this is a very comprehensive survey of what was the state of the art until last year. And there is also a course at TU Berlin that I've been working on, trying to follow the survey paper. And here you have introduction and exercises, and yeah, it's more if you want to get an introduction. And that's basically it. So I think I'm done. 10 minutes, and I think we should move on to the first session.
Guillermo, sorry, I suggest if there are questions for the speaker to write on the chat. So maybe we can summarize after each session in case.
Definitely, yes. Please write the questions in the chat. And now I pass on to Cornelia, who's chairing the first session.
All right, so we're going to start the first session. With each speaker, please giving a short summary of what you have put online, take about 10 minutes. And afterwards, we're going to have a panel discussions with questions from us and the auditorium, as well as we consider the chat. So our first speaker was Riyad. The floor is yours.
Should I share my screen? Okay, let me. So
yes,
if I understand correctly, you just go through the slides, right?
Maybe make a summary.
Yeah, of course.
Okay, so yeah, okay, sounds good.
Okay, so I'll do it in a nutshell, 10, 11. Okay, thank you so much for organizing this and for inviting me. And so the talk I gave was something called What Happened Over the Last 10 Years. And for those who just joined the community, where we came from, where we are, what's out there, and what are the challenges to, I believe, will take us to the next step. So as I mentioned, we are here today because almost 30 years ago, neuromorphs met on a mountain in Telluride, and their scope was to develop new sorts of hardware, new sorts of computation, and go beyond what people know of hardware and architectures. There's a nice book about it called The Silicon Eye that Toby once gave me, I think 12 years ago, I don't know, a long time ago. I still have it. And it's a beautiful story about how neuromorphic stream started. And when Carver was a young professor, and of course the biggest achievement back in the days was Misha's camera that makes the cover of Scientific American. So although we are in an engineering space, I think what these guys, at least the people who started this field, were doing is really to understand and bring what we do today as engineering as a basic science, which is, you look at something, you don't understand it. In our case, it's perception. And so you try to follow the normal lead of basic science, which is you observe, you try to understand, come up with math models, and then the application are huge, because if you look at the stars and you make statistics, that doesn't give you lots of understanding apart seeing that moon will appear there, the stars there. But if you understand the orbits and everything, well, you can go to much more fundamental things. It's a deeper understanding that opens path for other things. So honestly, I know most of us are engineers, but we have a unique chance here to make computer vision as a basic science, because from one side, it's exactly the same scheme. We have eyes and brains. You can record from it, try to understand it, model it, and then build things, which can be a camera in our case, or processors. And then the applications are huge, because if we change computation, well, we can change almost all our society, from networks, machine learning, autonomous driving, everything, BMI, looping back. So I honestly have always thought of Neuromorphic that way. It's a unique chance for us not to go, just to hold a line, which is my work conforming with the data? If so, it must be not that wrong. So why cameras? It's because retinas are what people believe the most approachable part of the brain. It has always been an exciting space for people to try to understand the brain. It's a 7-layer structure. It's very easy to record. This is, I think, my setup in Paris before I left. I mean, setup we share, and so it's very easy to record from eyes. So event cameras, it's a long story. I think started around 2000 after Misha's. There's been lots of work before. So there have been many attempts. And the one that reached us, I think, originates from Jörg Kramer's idea of differential signaling that has been then taken by Patrick Lichtsteiner, Toby, and Christophe to do the DVS, and then the extension of the DVS, which is the ATIS and everything that followed. And you see, it's really an incremental effort. And today, if we are here, it's because somehow the field made it, and cameras are becoming a commodity. I think you can buy cameras from all over the place. When I started, I mean, 15 years ago, there were only one place and then 2 places, and no commercial of any sort. So why is this a great chance for us? First of all, as I said, it's because somehow it mimics what the brain is doing. So you can read neuroscience and get insights of what you should do. And then the space is wonderful, because you see, when you, at least in the current thread of event vision, is every dot you see here is an event. This is times 0. Everything is new, you get the frame, and then every dot comes with X, Y, a very nice temporal precision T, and the gray level. And so when you see that, the main idea of, I would say, the historical path of Neuromorphic was to use this timing of these events and try to combine some computation between space and time. And the other advantage of these sensors is the really low bandwidth and low output. It's not really true with the last sensors, because last sensors are blowing really lots of giga events per second, even with compression. But you see here, this is a QVGA mounted on the car, and you have around 100 events per millisecond or 10th of millisecond. Sometimes it rockets, you have 800 events, but it's still much less data than this baseline here that is a camera seeing at 30 frames per second. So you see that the advantage of these sensors is really to try to find a way to process these events and never allocate memory to store everything, to go back to any sorts of frame. Maybe you can, but I think all of you know what I think of frames, but you'll see I've milded my position here lately. And here you see something really nice. It's a hand waving. You see when you, in blue, it's the number of events, just to show you what's happening. And you see the hand waves. The temporal resolution is so high that you see it slow it down and then accelerate again. And what really matters is here, what I put in red, which is if you were to allocate any type of deep network, a deep temporal AI network, and you would allocate all the planes and you make them work, you would see that your planes will be, for every database we use, 8% occupancy, 3%, 1%, 1%. So 99% of those planes are empty. And it's, again, another way, not only are you losing the advantages, but you also lose lots of resources. Yeah, so frames, why are they bad? All of us know that when you have a robot, you'd like to go as fast as possible, but then you will have oversampling, meaning you get information that are useless, like this background here, whereas what you're really interested in is the movement. And so if you increase the frame rate to get the movement, you will increase all the junk information you already have. And if you reduce it, you will reduce that static part, but you will miss the dynamic part. So it's really a paradox. You cannot go. You have to find something in between according to the powers of computation you have. And it's unfortunately very high power and high latency because you just have to take all the information out and throw most of it. So just for those who don't know, we are using images today as a history momentum that comes from this invention that it's called the camera obscura, the black room. It's a pinhole model, and it could have been lost in history, but what happened is that painters start using it to paint faster and make more money and move this box from castle to castle. And over the years, this guy has been replaced by pixels and this very sloppy and brittle optics by nicer, cheaper plastic optics. And that's it. That's why we use frames. And that's why even 300 years ago, 400 years ago, we just kept doing this. So today,
sorry, could you please keep it to 10 minutes?
Am I not 10 minutes? I have started at 11, 2 minutes and I wrap up, okay? Thanks, Cornelia, for the reminder. So the event computation today, I think, is split in two waves. People who advocate for incremental. Incremental means one event, one update. And it makes sense when you see what I just shown you that this is the way I believe to go because it's very low. But the other side is really to try to stick somehow to our past, which is frames, and generate images, do batches. And the main reason is we have the hardware. So to make it very short, I think the main problem we are facing today is linked to the arbiters. Maybe we can talk about it. I think Kobena has given a full talk just on arbiters. So the arbiter we use is very old. It's a hack found by Kobena, I think around 2001, that nobody ever challenged. It's this idea that if you want to compute with time and you want to take the information out of the pixels, a pixel must ask a request on the y-axis, on the x-axis, and if it's both acknowledged, goes out. And that's very costly. And most of the arbiters try to maximize their position, meaning if they took a pixel out here, they will tend to try to stay here and not go elsewhere where there is an event, and that scrambles time and that creates lots of confusion. So this is really, really bad. I happen to work with few sensors that don't do that, and it's really night and day. And the other big missing thing that we have to sort out is we need a good piece of hardware that allows us to write our equations to make use of the event-based. And currently the threat is to replicate what nature does. I think we've all done some sorts of Lohi or True North or whatever in our labs. And we know that today it's very limited cases. We don't know enough of the brain. I think that's it. The rest can be discussed when we are all together.
Oh, thank you very much.
You're welcome.
Okay, so our next summary would be then by Greg Kuhn, who will tell us about applications from the University of Western Sydney.
Thank you. Can I just share my screen quickly? That should work. All right. Hello, everyone. I'm Greg Cohn from Western Sydney University, from the International Centre for Neuromorphic Systems. And yeah, apologies if it's a bit later for us here. It's after midnight, so forgive me if I go a bit slow, if I mumble more than I normally do. So I'm going to talk to you today about a few things, a bit of a range of things, starting from some space tracking applications and going all the way to some of the more interesting and perhaps more fun type things we do, which is really building robotic foosball tables and robotic pinball machines. And I'll explain to you how we're doing that and why there's some science behind those tasks that we're doing. And I think the reason that we're doing this is that, and this is sort of core to what we do at ICNS, which is really start with an application, with a problem, and then try to work back from that. So how do we solve the problem with neuromorphic sensors or processors, and then the algorithms that tie them all together. And it's really nice to have a well-defined problem because it makes the rest of the system so much easier. You know, you can actually optimize everything when you know exactly the task you're trying to do. And I'll show you why that gives you some really big benefits. And by just changing the sensor, you can do things you can't do with conventional sensors. And we've leveraged that, for example, and primarily in this field of space situational awareness, or as it's becoming called, space domain awareness. And what that really is, it's really tracking objects in orbit around Earth and now in orbits around the moon as well. So primarily satellites, but a lot of space junk as well, because we've really been pretty bad about cleaning up after ourselves in space. And there's an enormous amount of debris in orbit around Earth, as well as all the satellite infrastructure that really makes modern life possible. You know, when you actually stop and think about how much of life is dependent on things that we have in orbit, this very fragile ecosystem of communication satellites, GPS, weather satellites, you know, it's all far away, very difficult, very expensive, and at risk of collision. And, you know, before we can do anything like legislate space or figure out how to share it more equitably, or even just go and clean it up, we have to know where everything is. And we do a terrible job of tracking it. And that's actually where neuromorphic cameras can help. And the reason is that the way they work actually lends itself better to tracking objects in space that are moving than conventional cameras. So I like to show the slide. This is actually the telescopes we started with when we put neuromorphic cameras on telescopes. This was about 5 or 6 years ago now. And the real reason I want to show it to you is that we're still not using sensors that were built specifically for space imaging. And we're going up against astronomy cameras that are really the pinnacle of optical engineering in some cases, and they're actively cooled, very expensive, very highly, you know, refined pieces of electronics. And when you look at telescopes like this, the most important part really is not the actual telescope tube itself, it's the mount that you use to move it. And they're all built around conventional ways of doing astronomy. And what we're finding is by changing the sensor and changing the way you use the sensor, you need different types of hardware. And we're actually going to now start building our own telescope mounts because we can't get this hardware to do what we want to do with it. So I'm going to show you this little video here, which is the first event-based neuromorphic recording that we took through a telescope. That's Mars. And this was 5 or 6 years ago. So we've gone a little bit further from there. This is where we are now by comparison. This is a star cluster of 47.2 UC. As you can see, we can see a whole lot more stars these days. And what's really interesting, however, is what happens when you move the telescope. So if I went and tapped it, for example, in this case we're moving electronically, but what you'll see when I move the telescope, I don't get motion blurring like you would have in a frame-based image. You'll see it here. I see the movement, but in fact, a whole bunch more stars pop out when I move. And that's really interesting because we actually see better when you're moving. So we break all the rules of conventional astronomy, right? And as a result of that, we can do things you can't do with normal cameras, and it enables ways of operating that people in astronomy just would never consider. And it's really culminated in these two shipping containers you see here. These are our AstroSight mobile neuromorphic telescope observatories. So they're a full telescope observatory built into a shipping container. And the reason we can do this is because unlike telescope observatories, we're probably the only people who don't mind a bit of motion. We don't have to sink concrete and stabilize our telescopes. We can have a little bit of vibration because there's a road nearby. And as a result of that, we can build them into a shipping container, which can go on a truck, a train, a ship, whatever you want, put it down, literally just plug in power, roof slides off, telescope comes up, it calibrates, and it can start imaging. It doesn't have to worry about where it is or how stable it is. And really by just changing the sensor at the back of the camera, you go from a static building to something that's far more dynamic, and we can show capabilities on top of that with these sensors that I'm going to show you some examples of that in a moment, that simply normal astronomy cameras just can't even tackle. And it's really all about doing things like this, tracking low Earth orbit satellites. This is a conventional frame-based imager. It gives you a picture every 4 seconds. And we're really interested in that bright object you see on the left there. That's the satellite. By comparison, if we track with an event-based camera or neuromorphic camera, you actually can see it continuously. So here's a similar object being tracked. You can see it's that dot there, but we can do things like move the telescope as we're imaging, and that gives us a whole bunch of power. You'll see the stars streaking through as we're following it, but we can actually tell a whole lot more because you're looking at a frame-based output of this. So we're moving the telescope around, almost drawing like an Etch-a-Sketch here. But in reality, that's a stream of events, and we can actually start even characterizing the object based on the information we're getting out of it. So in a second, I'm going to show you something that no one else has ever seen because I only made it today. But on the 26th of May in Australia, there was a full lunar eclipse, and we were watching with one of our AstroSight containers, and this is the recording. I apologize that it jumps around a bit. It's just got to do with the fact that the moon is larger than our field of view, and as a result, it's actually quite hard to track it without having to manually move it to keep the actual line that you can see forming across the bottom right there. That is the eclipse moving across the surface of the moon. And what's particularly interesting is you can see the line of the eclipse, but notice how you can see the part of the moon in eclipse just as well as you can see the top left part, which is not in eclipse. That's fully illuminated by the sun. So it's a really interesting, quite a nice demonstration of the high dynamic range and the importance of the independent pixels in neuromorphic cameras when it comes to doing satellite imaging. So yeah, this is, no one else actually has seen this recording. So something just interesting to show you. But now I'm going to pivot completely to robotic pinball, robotic foosball. Why we're really doing that, which is that one of the things I think we struggle as a field is conveying the benefits of our systems. And we certainly struggle with astronomy, for example, because all the metrics are based on frame-based imaging. And it's really hard sometimes to convey why your system doesn't do well on those metrics, but it's because they don't really examine the aspects of your system that you are exploiting or that you're highlighting with the way the neuromorphic approach works. And I think by building benchmark problems, challenge problems that take a specific task or defined task or application, if you will, and then uses that to demonstrate some way of ranking objectively performance of different systems. So we started off by building a robotic foosball table. And I guess that came about from looking at how we've gotten to where we are with data. And I'd just like to go through the quick sort of history of that, which is really like, it all started with something like MNIST, which is a great data set because it's easy to understand, it's simple, it's like your sanity check for any deep learning system. Everyone needs a data set like that you run through, which is why it was logical that we created a neuromorphic version of that. But keep in mind, it inherits the frame-based nature from which MNIST was created. It's not native to how we may want to use these cameras. And sure, we've tried things like in our lab, for example, we use an e-ink paper screen to convert data sets now, and that lets us do things like very light level. It's still a bit of a almost ham-fisted way of doing it. And then some of the other things we've done is create a data set specifically to address where frame-based cameras have troubles, so high-speed ones, like where you drop planes in front of a freehand in front of the camera, where there's time and speed involved. And those get better, but ultimately you want a real-world problem. So we start with foosball. I just like this as an example because this is a valid shot in foosball, and it's so fast. If you look at the 30 frames per second out of a camera pointed at that, and if you look in the last 3 panels at the bottom right there, you'll see that the ball's only in the frame for 1 frame. So you either have to go faster and generate more data, or you can't do it with frame-based cameras. So with the frame-based cameras, it should be an easy task tracking the ball, but you have to deal with all the real-world aspects around it. So once you have it in a real-world task, it's much harder than you'd expect because of things like this. This is actually some real data, and on the right-hand side you see 5 sort of sections I pulled out. Now what's interesting there is of those 5, only 2 are actually the ball. The top 3 are actually the players. So simple things like pattern matching just don't work on this data very well. And I think that's something interesting. So when you check it from an abstract problem tracking a ball, which is easy with neuromorphic cameras, to a real-world problem, it becomes far more challenging. And also some interesting research that shows that the way we predict the ball motion and what you'd expect, it doesn't actually happen on the table. The ball moves in stranger ways than you might expect. So just quickly to finish up, I'll just talk about robotic pinball. And essentially, we thought about foosball for a long time. We thought, how do you essentially figure out if you're playing foosball well? I mean, we can sort of subjectively tell, but objectively it's hard. So we moved to this robotic pinball machine, which is great because pinball has a score, and a score is an objective way of saying if you do better at pinball in terms of score, you're better playing pinball. And the great thing about pinball as well, it's a really simple game. You've got 2 buttons, and that's it really. It's all about timing. And that's the real key here, because you can't cheat. If your algorithm is fast enough, you lose and you don't get a good score. So it's an unforgiving application in that regard, and it's a really good way to develop algorithms and compare and contrast them because you have this absolute measure as a way of comparing them. So I think that's quite a quick summary, but thank you so much, and yeah, I'm happy to take questions during the panel session.
Thanks, Greg, and all the credit to you. You really have introduced the most cool applications for DVS. For those who don't know, I mean, Greg really started the whole space research. I think you mentioned that you met an agent from the Australian agency at a plane, at the airport, and that's where it went on. And I'm also have witnessed the excitement going on around the foosball in Telluride. It was definitely the most exciting project, drawing in almost everybody. Okay, but now we are moving on to signal processing. So Rob Mahoney is on from the Australian National University.
Yes, can you hear me? Yes, good. So it's, as Greg said, it's after midnight here, and in Canberra it's actually 5 degrees. So many of you are sweltering away. Well, it's nice and wintry here, nearly the winter solstice. I want to talk about fusing some frame and event data. And so I guess I'm coming from a very much an engineering point of view, not philosophical about, you know, event cameras for their particular change the world point of view, but looking at event cameras and frame cameras together from a robotics point of view, they're incredibly synergistic. So event cameras are asynchronous, frame cameras are synchronous, event cameras are temporally dense information, frame cameras are spatially dense information. Event cameras don't get image blur. Frame cameras, you have an adjustable exposure to be able to get, you know, absolute intensities at different levels. Event cameras don't image static scenes, whereas frame cameras do. Event cameras have high dynamic range where frame cameras don't. So the two sensor modalities from a robotics perspective are incredibly synergistic. And if you can fuse event and frame data, you should be able to have it all. And so, you know, images that are spatially and temporally dense. Now, obviously, you don't want temporally dense images all the time, but every now and then you do want temporally dense images and you do want information in places. So it is nice to be able to get that. You want the high dynamic range, and you want to be able to image both static scenes and highly dynamic scenes. And so there's all these applications in event cameras for phones, you know, augmenting existing imaging systems for all sorts of applications that are along these lines. So it's a very exciting question. So this is some of the work we've done, and the DSEC dataset came out just recently. And so I'll just show you some of the results that we're getting with the algorithms. I won't have time to go through all of the details, but the DSEC is great for us because it's a stereo event camera data set, but we actually don't care about the stereo that is being used in DSEC. What we're doing is we're taking the RGB camera and the event camera, which are effectively co-located, and registering the two cameras together, and then asking the question, well, how well can we reconstruct the actual scene? Am I still
Lost
going?
your sound.
No, I'm not connected. All right, I'll just change. Where's my camera? Oh, this was bloody hell. No, this is not going well. Let's turn it. Okay. So microphone, that should be right. Speakers, you should be USB audio. I can't hear anybody. That's
Robert,
Oh, we
We
hear
can
you.
hear you. We can hear you.
Robert,
1, 2, 3. Okay, I should be there. All right. Sorry about that, everyone. My headphones just died. All right. So we're in this situation where we can combine these two events, and as you can see here, the raw frame data from the camera is washed out, so it's overexposed in parts of the image, and in fact, in other ones, you'll see that you get blur. And the algorithms that we're using now with this data set are able to really reconstruct quite realistically the texture that's there in the roads, pull out texture in the backgrounds and in the image, which simply isn't there in the original image. And comparing to some of the state-of-the-art event-only constructions, you can see here with the E2 vid, there's a couple of problems that event-only reconstruction always has. One of them is getting absolute intensity information, and the other one is...
You're not sharing your screen anymore.
I'm not sharing the screen anymore, sorry. Am I sharing my screen now? Yep.
Yes.
Sorry about that. My partner is trying to sleep, of course, so I was trying to use my headphones, but then they died. So, all right. So I'll jump on to the next example just to show you that. So again, another data set from there, and here you can see one of the problems with learning algorithms. So you know, we're not being fair to E2Vid here. We're simply applying it to the raw data, but it's not particularly well trained for the DSEC data, and so it's just simply going to fail. And that's one of the problems with learning algorithms, is that they're just not, there's always a situation where they're just not trained for the next set of data. Similarly, the ECNN algorithm that we were running down here is doing a better job because it's trained on a wider set of data, but still not reconstructing. You can see that the filtering that we're doing is doing a pretty good job. So we're very happy with the results we're getting. And this is a poor example of what we're trying to say here, but this is the temporal reconstruction. So what we're doing here is we're reconstructing a frame exactly halfway between two frames. So in the top left here, we can see there's 2 frames of data from this old data set taken with the Davis, with significant displacement in pixels. And what we can see here in the reconstruction at an intermediate frame is we're doing a pretty good job of reconstructing. Even though we're using quite a lot of frame data in there, we're actually being able to cancel out the frame data. In this one over here, you can see particularly here, just on that edge there, you can see the previous frame as a sort of a shadow in the image, and that's a very common thing in trying to reconstruct temporal data and use frame data. So I'm because of my problem, I'm a bit low on time, so I'll do 2 slides and then I'll jump pretty much straight to the end. So we all know, I think, about events and what they are, and the fact that effectively what you're doing is quantizing in intensity, but taking real temporal information out of the event at a level. And so what really the underlying principles that we're doing is to treat that then as a continuous time signal. It's not a continuous signal because it's quantized in intensity, but it's continuous time. And of course, if you just take that signal and you do a real integral, a temporal integral of a signal where these deltas are Dirac delta functions, it's the same thing as the algebraic direct integration process that people do. And of course, that's a reconstruction methodology. The advantage of taking this perspective is that it opens up the principles of systems theory. So linear systems theory as a way of analyzing event cameras. And all we've done here is taken this expression, which is the integral of the events, and I've taken the Laplace transform. This really, truly is the Laplace transform of these signals, and you get exactly a transfer function representation of what to most people in event cameras is simply an algebraic summing process, but it actually has this linear systems process. And so direct integration, as we know with existing cameras, is really noisy. What we can do is we can do things like say, okay, well, we'll clean up the noise just by putting a high-pass filter on. So I'm just going to do it from a systems theory point of view, stick a high-pass filter on it, and that'll clean away some of the temporal noise that's coming in the DC area. All right, so the other thing that we can do is we might say, okay, we're going to put a high-pass filter on, but I can actually change the way I realize things like filters. And so this is a feedback realization of the same filter. So the transfer function that I get is exactly what I wrote before, but the way I wire that inside my algorithm is different. I wire it with this feedback loop. Because I do that, I get this ordinary differential equation at the bottom here, which is sort of underlying a lot of the work I do. Another thing you can do there is you can take frame data now. Here I've got my frame data, and it's low frequency, low temporal frequency, but I can add it in because the way this feedback loop works, it's sensitive to low temporal frequency data here and sensitive to high temporal frequency data here. And this is the principles of the complementary filter, which I worked on a few years ago. And we get a trade-off between the two. And I'll jump over a couple of these slides just to get to the main point. So the main point here in what I'm actually doing today is in the complementary filter, the actual gain that you use in that filter, which essentially tells you how to trade off, is a constant gain, is an engineered gain. And the work I'm talking about today is really about how to tune that gain in a sophisticated way. And so what we've done is we've drawn on the language of linear systems and Kalman filters to do that. And this is actually the main slide. So this is the algorithm that we're proposing. This part of the algorithm here is just a complementary filter, right? It's exactly the same as the filter that's been published already a few years ago. And what we've added to it is a gain tuning algorithm based on a stochastic fusion principle implemented through this thing called the Kalman filter. We need models, sorry about that. We need models of the uncertainty in the events and the uncertainty in the frames. I don't have time to talk about it, but it's in my other talk. And then we do a couple of other things. So we do a little bit of cleaning up of the signal first to get a bit more temporal resolution. And the other thing we can do if we want to is spatial convolutions, which people have done. And so what we get out of this tuning is it actually actively adapts the gain. So where you've got these washed out areas in the scene, it's trusting the events very strongly. And if you look in detail at this area, you can see it's a bit of a, a chunky sort of event reconstruction, but it's doing a reasonably good job. But here where it actually gets actual camera data, so there's actually reasonable intensity, even though it's quite dark, there's actually reasonable information there. And in that area there, it's augmenting the camera data to give you this high dynamic range resolution. And so we're getting these really good quality high dynamic range reconstructions out of it. And this is a video from the DSEC where the left-hand column is the raw vision, the middle top is the E2VID, the top right is ECNN. Whoops, I have to run it again to make it run. And the bottom middle is complementary filter. The bottom right is the asynchronous Kalman filter. We'll put this online so people can have a look at it. But the asynchronous Kalman filter is doing an extremely good job. So I'll quickly conclude and then hand over. And sorry about going over time. So I very much agree with Benison's first talk about exploiting the asynchronous nature of the sensor and the algorithm design. So everything I've done is really designed to be implemented asynchronously, although at the moment the hardware available, very hard to do that. So, we're still in sort of a temporal, sort of a problem in implementation. I think there's a really interesting problem in using frame and event data together, and I think there's a lot of really important applications there. So we're working at the moment on this stereo hybrid event frame data. The other thing is everything I've talked about tonight is shallow. So I'm just talking about these engineering algorithms effectively. And the reason is this one here, that I think we're in a period, a halcyon period in terms of the event camera sensors. So the quality of the sensors are improving so much year by year that as researchers in this field, I think it is necessary to really look at the fundamentals of the algorithm, not simply to learn from data to do better, but actually how can we build engineering algorithms that will work for any system so that the manufacturers can essentially just roll algorithms in that just improve the performance of what they're rolling out. So sorry, I probably went a couple of minutes over there, Cornelia.
Okay, thank you. Thank you. I think our next speaker from innovation is missing. Is there a replacement from the audience? Somebody, Toby, would you like to say something? Otherwise, we move on to the discussion. Okay, I assume not. There were some, Toby, yes?
No, it's okay. Go ahead.
Okay, so there was one technical discussion that I see in the chat pressing that hardware people got involved, and we need Riyadh to clarify this. So basically, what are the readout methods that you have used that are better than arbitration?
So
what sensors were those?
So there is a new class of sensors that are scanned, but scanned at very high temporal resolution. It's I don't know if you call it the hack or something else, but it's super fast. It goes 6 kilohertz. And then when you do that, you see that the pixel timing, the surface of events or anything is really smooth and nice. You still have noise, but it's nice and smooth. And times are really there. most of the complication when you want to do event per event, that's why people want to do batches of events or frames or whatever, is because times are very unreliable and you have to always regularize locally. So anything that can bring you perfect timing is good. And there was also a skin, an artificial skin that came to Telluride a few years ago. It was no noise, it was beautiful. So I started putting all the algorithm and then I removed all the regularization for time because times were beautiful and everything could work. So I think the future is very close to what Kobena is going to talk about today, which is this very nice 3D arbiter. But between the old arbiter that he has done, that everybody's using and not challenging since 2001, there is a long way to go. I think he brought it back thanks to this fence program and his other things. He must be around, right? And
yeah, I'm here. I'm here.
There he is. That's the guilty guy who brought that to Arbiter. No, I'm joking.
Yeah, it's not to that. Anyway, I put some clarification in the chat, but I didn't know about this scanner. So if you're going to be going at 6 kilohertz, how big an imager can you read out at 6,000 frames per second? I mean, it's not going to scale, right?
No, but it's for a certain resolution, it does the job, and it's still okay. It's still better than the old Arbiter, because the old Arbiter would stick somewhere, and then you would times here, and then you jump, and then you stay there, and you don't know. Times are completely scrambled.
That's the 2000 Arbiter. The 2004 Arbiter doesn't do that, and this is what Prophecy is using. So it does it's a fair Arbiter.
All of them. Yeah, I know Prophecy has improved it lately, but it's still based on your hack.
They're using the same design from 2004, which
everybody.
2000, yeah. But Riyad, let me just say, I'll get into this in my talk.
I know.
The reason why is very subtle, right? A lot of people are confused about this. So I'll try and sort of, if you watch my talk, I spend a lot of time on what's really limiting us. But ultimately, what's limiting us is that we have to put all this circuitry on the periphery of the chip. And then we have to drag these huge row and column lines. And it's just like so we have to do all these hacks just to squeeze performance out of it. But, there has to be a whole new approach, which I'll talk about.
Yeah, so just to tell you, the first stereo work we've done a long time ago, like around 2010, I had 2 cameras and I tried to match on timing, which looks really great if the Arbiter was doing a decent job. And then you would see that some pixel arrived here and some arrived here, and then suddenly they never happen at the same time. That's why we had to regularize. And that's the biggest problem. I think that's why people are sticking to frames more. But this is a beginning. So yeah, that's what I wanted to say.
Okay, thank you. So we're looking forward to Kwapena's talk later.
It's already online. You can watch it.
Okay. Here a few questions. Okay. As Riyad pointed out, the DVS concept grew out of biological considerations. Most work here on event-based processing has been technical. So where do you see opportunities for convergence research that ideally is bidirectional from science to computer vision, robotics, engineering, and vice versa?
All of us, for those who are computer vision, I see Costas here, and we've been around for quite a while, you also, Cornelia, and I think we've done the best we could with what we could with images and everything. And it's still engineering. Here, as I showed, we have a way to, neuroscience is there, and it's using the same format as events, slightly more advanced, more new things to learn. But that's the guideline, that's the data. My lab records from eyes and brains, but I think it's quite an oddity because, you record from things. If you get closer to neuroscience, you'll have lots of ideas because there is time. It's much more complicated than what we're doing, but there are answers there. I think all of us in the neuromorphic community, say Kobena, Ralph, every one of us know about neuroscience deeply to some degrees of knowledge. So what would you do if we had the opportunity to go away from engineering, which we will always be, we have all the engineering tool, and just get closer to the truth, It's this is my thought. And I think, see, when I talk with Kobena, we have deep discussion about neuroscience, although both of us, do technical stuff in engineering. And it's the same with many people. So that's, it's a unique chance for us. You see, it's a unique
So you
chance.
see that your hope is that more neuroscience will make better technical approaches?
Yes, of course. I mean, yeah.
In the design or better designs, Kwabena?
I think you need 3D. We're suffering to build a 2D, to use 2D chips to build a 3D brain. And all these
You need
problems
3D
eventually-
chips.
all these problems go down to wiring. We just don't have enough wires. And ultimately you have to fix that problem to get the kind of quality that the brain has and timing.
Kuben, I think what Cornelia tells you is how much from neuroscience you pick for your everyday work for
Neuroscience
inspiration.
is not relevant in 2D unless you can go to 3D. That's what I'm saying. If you put it simple.
But you do read neuroscience papers, right? As I know from you when you
No,
listen
I
to
mean,
your read.
I'm not mischaracterizing what you said. I do read all those things, but
I know.
The deeper I get into it, the more I understand what the problem is that we're trying to solve, which is very different from what I thought it was 2000.
Veamos cómo está la restricción igual, porque está muy brígido.
I think somebody's
Your point is if
Oye,
we go to 3D, we will eventually have even better designs.
No, then the way the brain is working becomes more relevant to the solutions that we need. Do you see what I'm saying? All these problems we're talking about is because we have to multiplex because we don't have any wires. Like, a ganglion on the retina, it's got its dedicated highway all the way to cortex. Nobody messes with it. It's got it. It puts the, there's spike time in millisecond time scale that's carrying information. Nobody messes with it. Right? If we have to, share wires, it's tough.
Okay, so what you're saying is forget about the classic computation and move the memory next to the computer.
I'm not saying that. I'm saying you need wires. There's no substitute for just more wires. You can fake it, but then you see these problems that Riyadh is talking about, you can't completely fake it, you're going to get busted. So that's what's happening.
So through wafer vias, down multiple layers of chips stacked on top of each other.
Exactly. And and we are starting to, anyway, I'll get into this, Maya. We're starting to do this now. Samsung imager, Privacy imager, they are 3D. There's 2 wafers, right? And so that opens up whole new things which nobody has exploited yet, which I'm going to show you how you can exploit. But
nobody, are you sure about that?
They are still using these arbiters we designed in 2D when we didn't have the 3D. That's what I'm saying. So it opens up the design space, and we should really exploit that. That's where you can fix these problems or start to fix them.
I think Coben is giving you the hardware side of it. From a computational point of view, you see a lot happening when you get the real data. This is what a biological retina, you put it on a dish, you shine a movie on it, you can get the spikes out, the events out. How does it work? It's the approachable part of the brain. That's why we call it. And you see a lot there. And you see a lot today because we've improved neuroscience tools. You have better recording systems. You see stuff. And that makes you wonder, which are events? And of course, you can go back to a frame, but it won't be optimal because that's not what the story is about. So yeah, from both sides, we need to get closer to neuroscience, just a bit, slowly, reading, looking.
For Rob, if you don't mind, now that you mention it. So in the DSEC dataset, Rob, I think you showed some sequences at night, and I think there's lots of burst noise from the lights, but I didn't see it in the videos. So how do you handle those? How does the filter handle those?
This is the, because the lights are actually flickering, right? So they're actually a flicker that's going on. So this is actually data that's been developed by my students. So I'd have to actually have a careful look at it. But I think what we've done is we've just had a bit of a look at which actually frames we're picking. So if you dig through the videos, you'll actually find that it does flicker a little bit in the actual reconstruction. So we've just chosen the reconstruction to blur that out so that you don't see the flicker in the lights. We actually have some other algorithms that we're working on with Davida from Prophecy for flicker removal as well. So, but that's a separate piece of work. Yeah.
Thanks.
Does that make sense? Great.
Thank you. So I will pose one more question. What have we been missing regarding the concept of computing in time? it could be, where do you see interesting applications that could profit from that temporal advantage? I think that's what it comes down. Riyad pointed it out.
I think, yeah, the game today, every time when I started my career, people would call us and say, can you solve this problem for us? Now I get the same phone calls, but people ask you, can you solve that problem for us for 1 milliwatt? They come with a power budget. It's the IoT, it's the 21st century. And we want to get rid of clouds and networks and have everything in one hand. This is our promise. This is where we should go, and this is where we should deliver, because we're low power and low latency. So those are the two words: low power, low latency. That's what the market wants. Anything you can do with consumer market in that field is going to make a change.
So low latency, okay,
Yeah.
application low latency. And I will to satisfy also our sponsors, whoever they are, ask one ethical question that was in the chat, especially for Rob. So now that you're fusing with images with DVS, where's the privacy? Where's the computing on the edge?
So where's the compute, or where's the ethics?
No, I mean that kind of look seems like going back to classic Internet of Things with everything in the cloud when we're going back to images. While one of the points was really keep it local, right? Edge computing.
Yeah, look, I think there were two things there. One is that I think if you have an event camera and it's a good quality event camera, then the image is there, right? There's no encoding that you can't reconstruct the image. So the privacy question that was on the web, I fully agree with. There was a comment there that if you've got a good event camera, then it's you need to treat that image with the same respect you would any image at all. The other question here is around, why are we looking at combining frames and events? And because I also agree with what Riyad's saying, is that I think there's a lot of benefits in just working with events, and particularly putting the compute onto the chip so that you get rid of transporting data, which is the really big power consumption, and you get rid of latency. So I agree with that, but I also see lots and lots of engineering applications in combining the two. I mean, that first slide I put up was just the synergy between traditional imaging and event imaging. So if you want to have an iPhone that can take a photograph of a motor car driving past, a meter away from you, or take a photograph in a disco and do this sort of stuff, people in iPhone companies and smartphone companies, they will be putting event cameras with standard cameras and using them to get really good quality imaging. And so that, I think, is a massive application domain that is of significant interest. And that's really, really what that talk from mine was about, very much from an engineering perspective of I see the application.
If I could just add something to that, because Rob's right, but I think I have the extreme of that, which is for the telescope work we do, we still use integrating cameras, because there are things you can do with integrating camera you simply can't do with an event-based camera. So they complement each other. And there are tasks where, we'll never get to the sensitivity of a 30-second integration with an event-based camera. It comes down to physics at the end of the day. So sometimes you do have to integrate. That you maybe, moving away from the biological inspiration, but if you want to do a task, the combination of the two unlocks things. So, for example, often whilst we're staring to do integration, we're using the event-based camera to catch other things moving through the field of view, and that information together gives us everything. Combining them is the trick.
Can I say something? I mean, when you look at the way the human brain works, the periphery of it, all sensors, is sub-millisecond precision. And the deeper you go with understanding, and it becomes slower and slower and slower. There are two parts of the brain, a fast one and slow one. So we're not denying the fact that frames are there somewhere. So you can call them in the very slow prefrontal cortex, because you see me, so you have a stable representation of things. And if you work on that very fast way, you see me, you see your mother, you see whatever, it's gonna flip. So you need stability, and that's where frames are. And I agree that there are some engineering problems, and we cannot, give back the past. But when you look at the data, at least for a lot of what we need to do, you don't need frames. Of course you need frames if you need stability, or if you do a deep layer, your last layer, even if you're doing time, your last layer must be slow because you have to, you know, get some stability in your visual system. But I don't believe, you know, apart from pure engineering problem, that anything apart from just showing an image is always be beaten by events. That's for sure.
Yeah, so an interesting comment on that, I can sort of agree with you. In these filters that I'm working, these linear filters, there is an internal state in the filter, which is the image, right? Now I'm stabilizing that internal state with an external image input. That's what's grounding it. But equally well, you could have a prior in there, or you could have an AI system that's stabilizing with semantic information, and that's essentially what the brain does. So, you know, I just think there's an aspect of processing here which is very temporal, where the events are very high temporal information, and then you can actually use linear systems theory to actually understand how the slow information operates in a sense.
Yeah, there are different timescales. I totally agree. Yeah, but I mean, just going from events to frames and doing whatever, I think it's useless. Personally, you'd better take a real camera or an HDR camera.
Yeah, but the real camera doesn't work in a disco. This is the point, right? I mean, there are applications right now where you can't get a camera to do it, and by combining events you can. So it's super exciting, you know. I don't disagree with the philosophy that you're coming, but there's some problems out there that are super exciting to combine the two.
There's an in between, guys, right? Which is you know what I liked about the ATIS sensor, right? Which is where the intensity image is actually triggered by the events, right? So you get this distributed image that is not frames, but it's actually a synchronous image of intensities. And so only places where there are particular interesting objects or moving objects and so on, those are the places where you would get the intensity parts. So you taking advantage of that also, I think, can have a lot of profound advantages, especially in the bandwidth and communication side of things.
So just to add, I think I've never seen another group than ours do that, but long time ago we've worked as events exactly in this point of view. You have an image, suppose a beautiful gray level image, and you just have one gray level that has changed, just one. What are you going to do? Are you going to do another Fourier transform on just one event or whatever? And so we show there is a class of algorithm that can do it that way and keep the image stable, which is exactly going and not offending anything from the incremental approach, which is you're computing something, whatever it is, it has to be stable. And every event comes and add to it. So you have two processes, one fast one and one that stays. And I think that's the way to go. Unfortunately, there's only one ATIS, and I don't think the company is doing gray levels asynchronously anymore. So I think Shoshone has one coming. Yeah, no, they're not. It's not on. I mean, I haven't seen it, but.
Okay.
Okay, thank you.
Thank you.
I think we are also on time, and
I think Cornelia, we were lucky, and Kainan was able to join after he had an emergency, and he wanted to answer something, but I think.
I'm sorry about that. Yeah, unfortunately, I had a bit of a family issue and only managed to jump in very late, so I apologize.
I think we are actually already on time. If you want to say just a few words about your video.
Okay. I think I won't bore you. I mean, I think I'll just make one comment about the this events versus frames thing. You know, there's the sort of the theoretical aspects, and then there's what the customers tell us, right? What they want, you know, what they tell us they want, which is not necessarily what we believe they should have, is they want perfect events with no noise, and they want perfect frames, and they want it from the same camera, right? And they don't care if we have all these beautiful theoretical frameworks. They just want beautiful engineering systems. You know, we of course can argue about whether that makes sense or not, but that's what they tell us, right? And so, yeah, the ATIS, I think, is a very interesting way, let's call it a sort of a biologically inspired way of getting grade level information. We, of course, have the Davis, which is, global shutter frames plus the events. I think the way to go, at least from the short to medium term customer point of view, is to basically try to give them what they want, right? Because that's what they understand. That's what they can work with right now. They're not going to throw away their whole ADAS pipeline just because we have some funky new technology, right? It's not going to happen. All the automotive guys, they tell us, yeah, we'll put it in our car as soon as you have multi-megapixel frames as good as the frames I have now. And so I think that's something which we have to work on, satisfying what the market's really asking for. Okay, that's my 2 cents.
ARTIS still allows us to do science, as Riyad pointed out. Okay, so thank you all the speakers, thanks the questioners, and we'll finish this first panel discussion and move on to the second one, session 2. So I will pass the torch to...
I think Davide Migliore and Costas.
That's you, right?
Yeah, I'm here if you want, no problem. So let me, I don't have the slide with the speaker, but I suppose now it's in the second. Okay, there is Bernabe, I suppose. Perfect. Please, Bernabe.
Yes, can you hear me?
Yes.
Okay, thank you. Yeah, thank you all for organizing this and inviting me. I'm going to be talking about mainly talking about event-driven convolutions. And I'm going to skip a lot of slides because this is longer, it's a bit long for 10 minutes, but I'm going to just skip a few. And but I will be, oops, what's happening here? Okay, so this is the outline. I'm going to skip the outline. This is about motivating frames versus events. I typically talk about Simon 1 spike per neuron system, but let me skip this as well. This is from Simon Thorpe, this 1 spike per neuron processing in the brain for recognition, which basically it tells us that information encoding and processing in the brain is highly information and energy efficient. This is the main message, because all the neurons involved in processing, they just spike once, 1 spike per neuron. This is what we want to imitate in hardware. So in hardware, we try to do address event representation. So here I talk about a little bit about the history and who is using AER, or basically all hardware SNNs, they use some kind of AER. And now next, I wanted to give a quick overview about the Caviar project, which is a European project that we had in collaboration with INI and also with Oslo University and some other groups in 2002. And it's actually where Toby came up with the first DVS, and in our group, we came up with the first event-driven convolution chip. So let me just go quickly while this is a web page. And here is one of the demos that we built. And here we see a recording. So this is the output of the DVS. It's captured with a special board. It is fed to a convolution system that tracks one of the circles with just doing one convolution with a circular kernel to do plain template matching. Next, it goes to a winner-take-all that cleans out the output of the convolution chip. And then this is used to center one of the circles in the center of the screen. So it's a closed loop control system. And we had a lot of fun building all these PCs and PCBs connecting with parallel AER port. And the latency of this closed loop was in the range of just a few milliseconds. So it was pretty impressive for the big setup that we had. So this was where Toby actually introduces, Toby and Patrick and Chris introduced the first DVS. But let me also tell you about our own DVS, that we developed sometime later, which we added just a little tricky circuit, which is shown here, to introduce some amplification in the voltage gain right after the photoreceptor. No? So it's a nice and tricky circuit that adds a gain with a factor n, which is the number of diode connected NMOS transistors that you have here. So in first order, it introduces no mismatch, but it introduces an important gain. Even if you cascade two of these, which is what we did, you get an extra gain of n squared. And this allows to have this overall gain, which is the ratio of the capacitors times n squared. In the original first DVS, they had a gain of 20, C1 over C2, this was the gain. So most of the area went in capacitor area, which is this reddish area here. With this tricky circuit, we could have a much smaller capacitance ratio and still have a larger gain, like almost 1 order of magnitude more. So in the same technology, we could build a slightly smaller pixel, but with 10 times better contrast sensitivity. Still noise was a little bit above the noise floor, but it was quite useful. And you can see here in this recording, these are two DVS cameras of resolution 128 by 128. And you can see that contrast sensitivity is quite nice. And these are plain events. It is not reconstructed frames. So this is just pure events, no, in JAR playback, no? the two sensors. And this was patented and actually licensed to Prophecy, and I don't think they ever used it so far because they didn't need it. But in case one day they need to have a much higher contrast, they can use this. The next slide. Okay, so now we go to convolutions. When doing event-driven convolution, here is, for example, a recording. We have an output of a sensor. There is a person juggling with 3 balls, and we programmed the convolution chip with a circular kernel to track the balls. And you can see here the outputs of the convolutions. The way this is done in one of the first AER convolution chips that we developed is very simple. Every time you get an event coming in from the sensor, you just project the convolution kernel that you want to compute, you project it around the coordinate of the incoming event. And then you have here an array of integrate and fire neurons, and by performing all the integrals of these kernels that you splash around the incoming address, you do it over time, and over time you get the convolution in time, in space and time of the input flow. So you get an output flow that represents a convolution event by event. This is the figures here correspond to the latest one that we did as an ASIC. We could allow an input event throughput that would depend on the size of the kernel that we wanted to store in the kernel RAM. We could store up to 32 different kernels, and the maximum size of a kernel could be 32 by 32. The input event actually is composed of the X and Y coordinate, the sign bit of the input event, plus 5 other bits to pick the kernel that you wish. So you could store five different kernels, and then depending on this 5 extra bits of the input event, you pick one or the other, no? And they all are integrated on the same map or the same array of integrate and fire neurons. And for example, this could be used for doing this processing here. This is a very simple processing illustrating the operation with 2 kernels. We programmed 2 kernels, this diffusive kernel and a Mexican head, which was performing a kind of winner-take-all competition. And then depending on whether the event was coming from the DVS or from the output itself of the convolution chip, we picked one kernel or the other. So the address event was composed of the XY coordinate and the sign of the events coming from the sensor, plus some hardwired bits for the DVS. And the output was again X, Y, and the sign, and another hardwired 5 bits to pick the other kernel. So all the events were flowing, and at the output you would have what the DVS was observing, which was a 5 kilohertz spiral on an old phosphor oscilloscope. Here we can see a 300 microsecond capture. Green dots are the outputs of the DVS, and red dots are the output events of the convolution, of the performing these two convolutions over time. Here we project in Y and time, and you can see that there is a very little lag, no, in computing the center of the cloud. So this is one application. Another is doing spatial convolution. Here, for example, is a vertical Gabor filtering. And this convolution processing has interesting properties. For example, it filters out temporal noise. And also when you do tracking, it filters out spatial mismatch. It has forgetting rates, so you also do temporal filtering. And the very interesting property is pseudo-simultaneity, because the input and output event flow happens almost simultaneously, because you compute the convolution as the events happen. So this input and output capture, they happen for the same 40 microseconds. So you have this pseudo-simultaneous property, and which scales up over multiple layers. And this is an illustration of doing a recognition experiment. We demonstrated that we could do 2 millisecond delay recognition, latency recognition. We also did it on Spinnaker. So here we implement different filters on Spinnaker. So the retinas coming here, we had an interfacing board that it changes the event to SATA format, goes to the Spinnaker board, comes back again in SATA format, and then to JAR for visualization. We use it also for stereo vision, because in stereo vision, by adding convolution, you add another clue for event matching coming from two different cameras. So this could be used for matching events from different cameras. And here I can show you. This is actually from Telluride. No, we had the two camera here and an object balancing, and this was then recorded and processed offline. This corresponds to another recording, not this one. Also here we were moving a pen in front of the camera, and we could do stereo vision and recognize and compute the depth of the events after matching and so on. And now let me just finish quickly with learning things. Here we used on Spinnaker this special temporal backpropagation on a convolutional neural network. We hacked a little bit the loss function. We added to the standard term, we added another term to optimize, which is the count of events inside the network. Ignoring the output events, just the events inside the network, and tried to minimize these. Depending on a regularization factor. And depending on this regularization factor, we could reduce significantly the average number of events in the system. And actually, if we compare this with a classification error, we can see that the optimum was actually for lambda equals 0.1, which is around here. So we got the optimum recognition for actually low internal activity. And actually the internal activity was about 0.1 hertz, which is similar to what the brain actually has in biology. And here are some recordings of what's happening. This was for a fully connected network, and this is for the convolutional neural network, the input layer coming from the NMNIST dataset and the output recognition. Another thing that we did was with STDP, we transformed, where we used, instead of using delta T to characterize the pre and the post synaptic time difference at the synapse, we used the order. This is something that suggested Simon Thorpe long time ago. But we also transformed this to restricting to 1-bit weights, because our motivation was to use this for memristors, which are in principle constrained to 1 bit. And in that case, we change the STDP rule to do a probability. If we are inside the window of increasing the weight, we just apply a positive probability to do a full change of the weight from 0 to 1. And if we are outside, we do a full change from 1 to 0, depending on this probability. And this we tested on a system, and we got some interesting findings. So here, this was implemented on an FPGA. And we implemented two versions, our 1-bit synaptic hardware version, and compared it to conventional STDP based on 8-bit synapses and 8-bit neurons hardware. The horizontal axis is the hardware complexity, the hardware resources. So on the same line, for example, for 1-bit, we could have 32 neurons, but for the same hardware complexity in 8-bit, we only could have 4 neurons. And you can see this blue is the 1-bit STDP. With 32 neurons, more or less, you get maximum accuracy. But for 8-bit neurons, you needed more hardware complexity. You needed to have 128 neurons. Actually, here I said it wrong. It's not 32, it is 256 neurons. But you need more hardware complexity to get the same accuracy. And regarding spike count, also the 1-bit system had much lower.
Sorry, Bernabe, we are running time.
Sure, yeah, this is actually
yes.
the last slide. So, okay. So these are the conclusions, and here I can stop. Thank you very much.
Okay, we can proceed with the second speaker, Professor Boheng Kwabena.
Yeah, hi, David. Let me share my screen for you guys. And then I'll start up the slide presentation. Okay, I'm sharing, and let me put up the slides. And let me start my timer. Okay, so yeah, so this is work I did with some folk who graduated 2 years ago, is now CEO of a startup called Femtosense. And I need to be in the right window, yeah. And so I put these two slides in just for you guys to follow up on the discussion. And so just real quick, this is actually from Eric Rieu's from Samsung's presentation slide from 2019, where he compares a VGA resolution imager with using a Arbiter for the column selection versus a scanner for the column selection. And the point here is that this Arbiter from 2004, my 2004 paper, does a breadth first search of the tree, which fixed the problem with an earlier version that was the greedy Arbiter that would service the same pixel again and again. But in this version of the Arbiter, once it services this pixel or this column, it won't come back to this column until it serviced all the other requests in the tree. And this is done by latching the states of the daughters of each cell, when you make the decision. And so in the limit of high throughput, where all these columns are active, the Arbiter just goes down, goes up 1, goes down, goes up 4, and goes down. So it becomes approximately a scanner, So you can see that here from Eric's, so the maximum throughput is similar. As you will see here from measurements, this is nice data from Samsung on those two versions of that VGA Arbiter here. And you can see at, out to like, giga events per second, they are using this sort of grouping strategy to encode more bits, less bits per event. The throughput is similar for the word serial AR Arbiter in red and the scanner in blue. But you can see in this, for very sparse activity below 6 million events per second, the Arbiter, actually, you can't even measure its latency, right? The latency is really short here. So it's better. And then it crosses over to where the scanner is better around about 6 million events per second. And it could be 3 times worse, okay? And this is coming from, it's not exactly a scanner. It may go up 1 or 2 levels and before it comes back down to pick the next guy. So there's a little bit of overhead here. And so what people have done is, but just to point out, the other thing that's also affecting performance here is the generating the column address, right? This is actually in the critical path because we are doing arbitration and then we are selecting a column and then we are putting out the address of that column, right? And so this as the number of columns become more, higher resolution, we are driving more capacitance and we are slowing down, that process slows. And so these this design hasn't been able to exceed something like 50 million events per second. And so this is a problem that, as we get to HD resolution, like you see here with Prophecy's latest chip, and Samsung has also addressed it similar but different ways. We have to sort of like break that bottleneck introduced by the encoding the column addresses. And so what you're seeing here is actually both of these latest chips, 3D, there's two wafers that are stacked. One is a 90 nanometer backside illuminated CMOS image sensor technology. And the backside where you put all your circuitry is in 40 nanometer CMOS. And they've got some nice results, and they can read events up to a giga event per second by basically using as little as 1.6 bits to encode each event. And but you can see basically the same architecture going back to that 2004 paper, where you read out these columns in parallel. Once you select a row, there's no acknowledge per column. Instead, you just acknowledge the row selections that you've got the data, and it closes the timing via the redrawing the column selection, the row selection. And so then the way they get around the bottleneck from encoding the column addresses, they don't do that anymore. They take the parallel data from that row and they pass it through this event signal processing pipeline. And basically they timestamp the data as soon as it comes out that row at 1 microsecond resolution to basically hide any kind of timing and delays and so forth from buffering and processing. And then they do this sort of clever spatiotemporal compression to get it down to 1.6 bits per event. So if you have a 100 megahertz interface, 16 bits, 16-bit parallel, 100 megahertz, you can read a billion events per second. So that's the state of the art. Now, what we proposed 2 years ago was that let's move away from this, hacky stuff we've been doing since the late 90s, where we put all of this circuitry on the periphery, and let's move the circuitry inside the array, because the bottleneck really is driving these wired ORs or running along sort of the column encoder. And so we propose basically, now this is possible with the 3D approach, right? Because your lower chip with all your circuitry, you can now put circuitry where the pixels used to be, because the pixels are now on the top die. But none of these Samsung or Prophecy is using this approach yet. So I just want to let you know about it. And so the other advantage of this approach is that you can see here, we've got what we call an H tree. And instead of assigning column addresses in red here and row addresses in blue here, which we then encode after we've selected the row and the column, here we are generating the bit of the X address, for example, with this node here. If it reads an event from this pixel, then it just sends up a 0 in front of that data, or a 1, and then this one sends a 0 or 1 and so forth. And so by the time you get up the tree, you've got all these bits that have been generated as part of the, in parallel with the arbitration. Okay, so then you can basically solve a whole bunch of problems with this sort of, what's called arbitration, but it's not really arbitration. We're still arbitrating here. It's just a better architecture where we are not driving these huge lines across the chip. Okay, it takes care of this race in the row of pixels, match delays in the columns, poor scaling of the wide ORs. And again, encoding addresses while you're arbitrating allows you to remove the encoder from the critical path and take care of races that occur in the arbiter tree. So watch the full talk if you want to know more about this. I go through this all carefully, but I'm just going to show you some results, in the last 2-3 minutes we have here. So this is the chip that we did, a 2x2 millimeter chip called Brain Drop. We are using this much of the core area to implement in 28 nanometer FDSOI, this ST's process, 4096 spiking neurons, 1024 synaptic filters. It wasn't actually designed as an event imager. It was designed to actually do, implement these sort of spiking neural networks. And there's weight memory and some additional memory for buffering events and reconfiguring the connectivity between pools and so forth. But the part that you're interested in here, relevant to this talk, is here we call what people used to call metapixels, now have 16 spiking somers and 4 synaptic filters. You can see the somers here and the synapses here. Because of the capacitors for filtering, they take up more room. And just to walk you through this, so now if you actually put back the metal layers, you start seeing some structure here that suggests that if you remove everything but those 2 levels of metal we're using to route events in this bit serial fashion, you can see we have 2 H trees. And one of them is basically has these sort of 6 levels that it's a 4-array tree. So it needs 6 levels to be able to handle 4 to the 6 to be able to handle 4,096 spiking neurons. And then there's a receiver that's sending events into the spikes into the synaptic filters, and also programming some local memory we have in there, which so has to address those 1,024 guys. And so this is showing you the the 4-array tree here with 6 levels for the transmitter, 5 levels for the receiver. And the way that we are communicating is we are using 1 of 4 encoding, which tells us which of the 4 daughters or children we are to send the event to, or to encode the event from. And then we've got some extra signals, handshaking for the start and the end of the packet. And so you can see, get some ideas. So all this circuitry down here is implementing that H tree. And these lower level nodes of the trees are sitting here dedicated inside the metapixel. And then the rest of the levels of the tree are routed up. That circuitry is placed in these cutouts. And then we route that together like you saw when you were looking at the metallization.
Sorry to interrupt, 1 minute.
Okay, thank you so much, David. I think I'll be good in a minute or so. And so, so this is just showing you the process in simulation from the extracted layout, where this a neuron in this pixel down here, actually 2 of them requested down here, and we are not pipelining. So we have to generate all these bits sequentially up the tree and so on and so forth. And you can see it here at the top of the tree, where we just communicate with the root. We cycle very fast, and then as we wait for more bits to come out from lower and lower levels, we cycle a little bit slower. But even then, we're able to transmit 23.5 nanosecond cycle time, which is about 40 something events per second. And so we've proven this concept in actual silicon, and it's like rock solid. There's no flakiness at all. It's fully delay insensitive. We're not making any timing assumptions. We're not cutting any corners. And each link is just 1 sender, 1 receiver. So that's fully delay insensitive. And so this is a NAP to transmitter on the order of 650 events per second in a 2v6 by 2v6 array. And there's a lot of room for growth. This is like where we were back in the 90s with the early versions of the Arbiter design, which improved tremendously. I think there's a lot of potential here, because now we have all this area next to the neurons to route stuff. So there you can watch the full talk for more about the prospects for this approach. And I would just like to thank ONR and Gray Matter AI Labs for funding, and acknowledge Crystal Push for privacy video that I didn't get the chance to show. You can watch it in the full talk. And this is the citation for the paper, and this is the GitHub with all the HDL for the design.
Thank you very much. I ask the third speaker, Ralph, I think Cummings.
Yep, I'm here. Okay.
I suppose we see the calendar, not the presentation.
I'm sorry, say again?
We see your calendar, but not the presentation.
Oh, yes, right, because I think Kobena is still...
I stopped, right? Oh, sorry. Oh, yeah.
Kobena, we know all your schedule now.
All your schedule now. We're going to do lunch tomorrow, man.
Yeah, my schedule is pretty relaxed, yeah.
I see you have a Jedi faculty team. That seems quite intriguing.
It's called for Justice, Equity, Diversity, and Inclusion.
Oh, okay. That's a sexy name.
That's important. Can you guys see the front page?
Yes, sure.
Okay. Wonderful. So thank you so much for inviting me, and thank you so much for giving me this opportunity to talk a little bit about some of these spike learning saliency modeling that we've been doing. This oops, you shouldn't have gone there. This talk is work that my student Khalid Abumeri is doing, and I'm just trying to be Khalid and explain the cool stuff that he's working on. So some of you may know that for the past few years I've been very much involved with Ernst Niebuhr and Rudy van der Heydt, and trying to understand how we understand objects that we look at and why our eyes are pulled into certain directions and look at certain things. Typically, basically, that means that we have these, what we refer to as a proto-object based saliency model, which starts off with some kind of retinal model, which has intensity, color, motion, information that then goes to a V1 model that breaks these this data into orientation, into edge, into texture, disparity, and so on. And then there's a layer that represents more what happens in V2 and V4, which has a competitive border ownership representation, and then ultimately a grouping approach that puts the saliency marker, if you will, on the object in the scene that is most likely to grab the attention of the algorithm, right? So we try to mimic as much of what we know about biology, and we try to implement that in with computation. Basically, these are MATLAB models that we are running. This is not hardware in this particular example. So typically, then what you need to do, then you start off. Whoops. Why is this moving forward on its own accord? Hold on a second. There we go. You start off with some image. You have had some humans watch these images, and you come up with a gaze map. Where do people look? And that's what this second image here is. And what we then do is our model tries to predict what the humans are going to look at, right? And the correspondence between these two images are what tells us how well we're doing. So this is all good and well, and everything that's been done so far has been basically videos, right? But what we wanted to do is try to do the same thing, but now with spike data. The question is, what drags our eyes when we look at spiking data? So for that, we were fortunate to be allowed to use this data set from Prophecy, which corresponds to two particular scenes where, let's see here whether this will run. Okay, why is it not running? And why the top one is not running, okay? Anyway, it's essentially just the data that one corresponds to a car driving through the city, and the other one corresponds to a camera, ATIS camera sitting on the side of the road and watching the motorway as it goes by. So we wanted to basically then try to build a saliency model that would use the spike data. So one of the front parts of your saliency model is this spatiotemporal filters that are either part of your, basically your retinal model, or at least at the very early stages of your saliency model. And a couple of ways you can construct this is basically to say, look, I know what I'm looking for. I know I like vertical lines, horizontal lines, maybe some diagonal lines. These are the different oriented filters, and but now oriented in space and time. So there's motion embedded within it. And I could handcraft it, meaning that I basically use something like the Bohr filters, and there you go, and I can make my models run with those types of inputs. Or I can develop a learning approach where I'm basically going to say, look, the data itself should dictate what the models of the filters, the spatial filters, should be. And then the question is, how do you learn these filters on data that is continuously streaming? Because we know that as you start learning things on real life learning, you tend to lose information over time, right? Because the thing that may have reinforced a particular spatial temporal filter may not exist later on in your video sequence. So how do you prevent catastrophic forgetting? How do you prevent how do you keep the relevance of the filters that you actually have left? So for that, we basically use an idea that came out of Joshua Vogelstein's lab at Hopkins. He refers to it as lifelong learning, which essentially has a set of competitive ideas or collaborative ideas where you basically talk about what has happened recently in your data stream, your event stream. What kinds of things do you prefer? And that's your recency estimate, if you will. What kinds of things do you want to keep no matter what's going on in the scene? So maybe you always care about keeping tracks of where all the cars are, so I don't get hit by cars. So that would be a robustness estimate. And then the other thing may be relevance estimate, which is, look, I only care about red cars, so I will ignore everything else. So that is something else that can be imposed on top of your learning of your filters, so that what your filters that sticks out at the end of your learning process would be those that would be, hopefully, relevant to your job, robust to the various changing data streams that's coming in, and also has some top-down control over what you want to do. And you can look at the paper, you can look at some of the algorithms a little bit later on as we go along. So from there, we can basically learn different kinds of filters at different resolutions and different depths of computation. What happens is that there are some filters that tends to stick around and are tuned to basically, if you could say, the more repeated aspects of the scene, and those are usually at the top right, top left-hand corner of these arrays, and those will happen to have a lot of variability and show up very rarely are those that are at the bottom right-hand corner of the two different set of filter models, right? And what the top one, like the top left-hand corner of filters essentially track is, as I said, things that are always, as part of your data stream, part of your event stream. So it could be, just cars in general could be a filter that would be seen by the one on the top left. But if there's a guy one time walking around and scratching his head, that might be seen only by the filters that are specifically tuned to a particular event that is very rare that happen, or a particular group of events that come in very rarely and can be can be detected by those types of filters. So then the question was, all right, if I have those types of filters at my front end of my saliency model, how do I show these two examples, right? One that is triggered by events that happens a lot, and one that's triggered by events that happens very rarely. So what we did, we basically had a hypothesis, and the hypothesis was that if I've been, looking at these events images for a long time, then I'm basically a experienced observer. I know what to expect. So I tend to be less interested in things that I've seen many times. Maybe I care more about what's going on in the background over there instead of all these cars going back in the front. So those would be referred to as an experienced observer. An inexperienced observer will be the guy that first takes a look at these images and they're looking everywhere. They're tracking all the different objects. And what we did is we basically gave these videos, we piped these videos through a headset, and we had Khaled, who's been looking at these videos ad nauseum, and tracked his eyes movement and had him just watch those videos. And then another person in the lab who had never seen these videos before, at least had not seen it very often, and we tracked his or her eyes. And then we basically asked which one of these two filter models predicts their eye movements the best way. So the top one would be what like basically the experienced observer would what they would look at. The bottom one here would be what the inexperienced observer would look at. But the data that really captures, our hypothesis, if you will, is that little confusion matrix on the bottom here. Basically, it shows that the green filter is one that basically tracks the inexperienced observer more, as we had predicted. whereas the red filter tracks the experienced observer more, because, as I said, the experienced observer may be more interested in looking at the nuance in the video streams.
So sorry, Ralph, the time is running.
Yep. Okay, yeah, I'm about to be done. So just to explain to you what the video is showing, the big dot, the big yellow dot, that's the actual eye fixation point, whereas the little green and little red dots are what the algorithm is predicting what the location should be. So just to finish up, move on to the next. So basically what we're doing now is that, there's no, as far as I know, there's no saliency database that is that uses spike images as input and have had humans observe them and a saliency database be constructed for them. So we are in the process of doing that with a HTC Vive, because it takes out a lot of the variables in the psychophysics experiment and makes sure that everybody basically looks at the same scene in the same way, and makes life a lot easier for collecting data of that sort. And our initial hypothesis seems to be working out based on this learning of these filters dynamically, and and we're hoping that as we build this database more broadly, it'll be something that'll be available to the community, of course, and it'll be something that'll be able to try out a lot of different types of saliency algorithms on it. Okay, that's it. Thank you.
Thank you very much. Thank you very much. The next speaker, Ignacio, are you there? Okay.
I'm here. Hold on. So I'm going to share the screen. Let me know if you can see it full screen.
Yeah, we can see it.
Great. So thank you very much, David. And thank you for the opportunity to the organizers. So I'm Ignacio Alcibaray. I'm with the Vision for Robotics Lab at the ETH Zurich, and I'm going to be talking about our research towards asynchronous SLAM with event cameras. So event cameras really offer a unique opportunity for robust perception and robotic applications, just because they react really fast to changes. They have HDR capabilities, and they consume really low power. But for us, the most important aspect of it is that they produce an asynchronous and sparse output, right? So this implies that there is no notion of time discretization, and there is only capturing of things that are changed in the scene. This, in principle, is a disadvantage, as in we cannot apply any of the traditional computer vision algorithms to these sensors. But to us, this is more of an opportunity to design novel algorithms that are specifically tailored for this kind of sensing modality. So in particular, we are going to be tackling the SLAM problem. We are going to take as a reference a traditional feature-based pipeline in which you will take some images and then detect some features in those images, apply some data association to produce tracks, and then later on get for a state estimation stage in the visual backend. If we take this into an event-based approach in an event-driven pipeline form, the initial point will be now a single event. So this single event represents a small intensity change at a pixel. This will lead to a change on the feature set that we are considering, and each time maybe removing, maybe adding some of them. We are consequentially also the tracks of each of the features has to change at least a little bit. All these changes build up to a incremental change on the pose, for instance, or the local map that we are considering. We are going to be talking about different works that we have done in this area, specifically about the visual front end. And you have to keep in mind that we are doing event by event processing, just each of the events individually. And all of this that we are going to show is meant to be running real time, CPU only in a single thread. So at least to some extent. Talking directly for feature detection, we can go to asynchronous corner detection. So keep in mind that the events obviously are getting generated around the edges of the scene. And we are using a surface of active events in this first work that we published. At the end of the day, we are just accumulating the latest timestamp of each of the events into the pixel that it was generated to. Then what happens is that every time a new event comes, then we are checking what's the local surface of active events, how does it look? And based on this, we can classify this incoming event as a corner or not a corner. The important thing is that we are doing this as soon as the events are generated. So there is no latency between the generation of the events and the classification of this event as a corner or not. And you can see that from the initial string of events that is already quite sparse, we can get into a more sparser, even sparser event stream of corners. Most importantly is that we are still inheriting the temporal resolution of the original stream. So compared to a normal frame-based detection, feature detection pipeline, in which you will face gaps between these detections in the image plane, in an ideal world, at least, the event-driven detection will be forming a continuous set of detections in the image plane. And we can exploit this to get really nice and simple data association based on nearest neighbors. If we translate this into a temporal space, this simple data association forms some kind of a graph or made of small trees that we can further process in an offline stage to retrieve the feature tracks. This will be the results that we see in high speed, and this method works fairly well, even despite the simplicity of the data association. But obviously, this is limited in its application for more complex scenes, yes, where the corner detections are really more cluttered and the data association is not as simple, or just simply you are missing too many detections. And then obviously this method is going to be not so good on that. But just to summarize, this initial work that we presented, it was about corner detection, really efficient, and some kind of really simple data association that we are going to actually improve in the next work I'm going to talk to you about. So in this second work that we published in 3DB, you have to understand we start with the corner events already detected by whatever corner detector you want to choose, but at event rate. And then we are going to again look at the surface of active events surrounding this incoming corner event, but instead of using for classification, we are going to use it for a lightweight descriptor, something that we can compute on the fly really efficiently. And then we're going to still do some kind of data association based on proximity. So you can see that we are growing some kind of a tree, but in this case, some of the data associations can be early rejected based on the descriptor distance. Each of these trees will represent a feature itself, but sometimes the branches will indicate that maybe there is a possibility that the feature has moved to a different direction. This is, we are keeping a multi-hypothesis approach to the features. And at some point, we have to decide what happened with these branches. Is it a feature in its own, or it's something that we have to discard? And this will be based on consistency. So with this, you see here, this is the full graph with all the branches as they are generated. Again, real time for this specific scenario because it's really efficient. From this graph, we can process now on the fly, online, a set of tracks that are checking for consistency and based on this descriptor distance and so on. So with this approach, we get way longer tracks than with the previous approach, just because the data association is more reliable. And if we look at the larger set of feature tracks, we can still infer the motion of the camera out of this. So to summarize, we have proposed a very simple local descriptor for these corner events. We have some multi-hypothesis data association approach, and we can retrieve the tracks in an online process in contrast to the previous approach that we did. The problem here is that we are continuously relying on corner detections in order to feed the tracking data, right? And then we are linking the performance of the tracker to the performance of the detection. And this is in general a bad idea, because if your detections are not so good, then your tracking cannot perform good, even if it's a really good algorithm. Our next work is actually dealing with this and moving directly to track on raw data, on raw events. So consider that we have a feature, and this feature is defined by a state. That is the XY pixel coordinates, orientation maybe. And then we're going to consider a window of latest events surrounding this feature. So from this, the combination of both things, we can define a projection, what we call the model. And this projection is to be matched to a template that we are generating only from the events or on the go, on the fly, okay, not something that is pre-computed, according to some alignment score. All of these elements form together an optimization problem in which we are trying to optimize for the best feature states according to some alignment score function of choice that combines the template with respect to the window of latest events. The problem is that we have to solve this at 2 million of events per second. Well, nowadays even more, giga events. But this is obviously infeasible to do for real-time applications or robotic applications. But if we take a closer look at the problem, and we understand that the event stream is continuous or almost continuous in the information that it's providing, if we were to solve this problem, the optimization problem, every single time, this feature track will describe a continuous trajectory in the image space. And we can actually exploit this the same way that we exploited in the previous works. So we're going to take the first initial state as the current optimal state, and we're going to spawn a set of hypotheses surrounding it. What we are going to do is actually only evaluate the solution on those hypothetical states. On those hypothetical states, the evaluation is really cheap, or way cheaper than solving the optimization problem every single time. And when we go to a new hypothetical optimal state, we spawn a new set of hypothetical states surrounding it. This is a much more efficient way to deal with the problem. Although the result, it will be in a discretized state, we can always revert back to the continuous formulation if necessary for better precision. The problem is that, we need to still do this at event rate. Keep in mind that we are processing event by event in this case. And when we are dealing with real data, then this is the velocity that it has to reach. And this is not so simple because every time a new event comes, we are changing the template, we are changing the event window. And in the initial approach, we needed to compute the alignment score from scratch every single time. In a second iteration of this paper, we decided to propose a new incremental rule that allows you to compute the incremental alignment score based on the previous alignment score and just the contribution of the latest event. So more in a event by event processing fashion. With this, we have like way better tracking than with the previous method, and we still have super good efficiency, and we can do high-speed tracking as well. And compared to other methods from the state of the art, for instance, this is from Sue, I think he's among the listeners here. You can see that previous methods, or the majority of the methods, still do some kind of batches, and they process the data as in frames or artificial batches, and they create tracking iterations, right? Essentially, we are reverting back to some kind of frame-like processing. In our case, we are advocating for a fully asynchronous tracking method that profit directly from the way that the data is generated, and you can update the tracks exactly the moment that the events has been generated without any delay. So just some final remark. Oh, well, no, sorry. So these last works that we were showing, they are about tracking, but only on raw events. We have achieved that to have real-time capabilities with the last changes. We believe that all of these elements already put us in a really good state to address the state estimation from an event-driven perspective, but this is ongoing research so far. So just to conclude some remarks, my personal opinion on this is that processing event by event or in an event-driven fashion is the natural way to go with event cameras. And in this regard, I'm kind of aligned with Riyad, his school of thought. I think exploiting it this way is the way that we can actually exploit explicitly the sparsity and synchronicity of the data. It also reduces a little bit the assumptions as in trying to tune for the motion of the speed or the amount of texture that we are going to expecting to see. But the drawback here is that we have to be really careful about designing the algorithms so they run efficiently. They are enough to run in real time. They are robust enough because we are incrementally adding only one event at each time. And they are scalable because now we are facing that every single year we have higher and higher resolutions, right? So we need to keep it scalable. So that will be all from my side. Thank you very much for your attention.
Thank you, Ignacio. Guillermo, I think we have finished the time for the slot. I don't know if you have time for questions. Let me know if I have a time for one question.
Yeah, I think we could just move the shift and use these 20 minutes, and then we start 10 minutes late, and yeah, make a shorter poster session. I think we're fine.
Okay, so there are some questions in the chat. They already answered the last one from Ignacio that is not answered is that is the state estimation also synchronous?
So the part that we have shown so far, it's about the visual front end, right? The visual front end is all the works that we have proposed is about tracking and so on, right? In that regard, the state of the tracker, it is asynchronous, but I suspect that Costas is aiming to get an answer from the backend, right? Like how would you actually do the processing on post estimation and map estimation? This is the part that is a little bit more tricky these days, and we are trying to figure out how to do it in the best way possible, right? We have seen already works actually from Costas about the Kanban filter and so on, but there is still a lot of flavor that we can add to this, and as I said, ongoing research for sure.
Okay, there is another question for Ignacio. Sorry, they're asking if since in the stream the appearance changed, they said it is very complicated to do data association. we can rely on this kind of tracking events?
Yeah, I think it's a really interesting question, and I will argue that the most complicated part for these algorithms that are meant to be computer vision approach, as in try to estimate the motion and so on, is that we have relied for so many years on the fact that every representation that we are faced to is static, right? That in this case, what we are seeing from an event camera is not only the static, it's also part of the history of what you have seen. You encode the motion on top of it. And it is true, I completely agree with this question. It's like the most challenging part is actually deriving a, how to say, a static representation of what you are trying to match. And this we do, for instance, in the tracker with this kind of template that evolves over time. And it's required to fixate somehow this. I think this is connected to what Robert was doing in his talk, right? How are you going to come back to somehow a frame, right, that you can rely on, right? But generating this data from event data is way, way more complicated, out of question.
Okay, there are other questions for Ignacio, but I would like to ask something also to the other speaker. In particular, I have a question because in the first panel, we discussed about the idea that we need the temporal resolution, but the trend now is that the resolution of the camera is growing. And so also the event rate is growing exponentially. Now we're talking about 1 giga events. I saw that OmniVision is presented the 2 megapixel event-based camera. And what is the approach? I mean, I'm talking also for Bernabé that is working with the convolution neural network, or Quabena that is presenting the Arbiter. How do you face this trade between the increasing resolution, the low latency, and the low power that we discussed before? If you are facing this kind of problem in your research, of course.
Yes, and in our case, what we do is we just try to increment the number of interconnection buses between the different computing modules. For example, inside an FPGA, you can have many convolutional modules that work independently, but they connect to neighbors with communication buses, and then the more you have, distributing also the traffic. No? And you can do this at the FPGA level, at the network on chip level, or at the
this means that also the FPGA should be more powerful.
Well, not necessarily. It depends on the complexity of the modules that you manage to synthesize.
Okay. Okay. There are another question for Ignacio. I'm sorry, because the people are chatting. It's nice because it's very interactive workshop. How does your template method handle? So for Ignacio, how does your template method handle template when the motion is parallel to line in the template, and so do not generate any events? Do you update the template?
So. I mean, obviously, we have to find a trade-off with this, right? If we look at works, for instance, from Gehrig et al., right? They will use a template from the images, and this is static, right? And then you have the edges that you are not going to see that are already encoded in your template. In our case, we cannot rely on that, and then we have to adapt to it. There is a way that this template that is initially generated is not as we saw it in the video, right? It evolves. So it has to adapt to those changes, and maybe sometimes you are not seeing the edges as they are initially generated, but you have a way to adapt to things that are happening. This way you can update the template on the fly. This leads to a variety of other issues, out of question, but it's a compromise that we have to adapt on the fly, for sure.
Okay. I don't have another question, I suppose. There is another question for Quabena about H3, but he's answering on the chat.
I have one. So in
please.
this session, we have two tracking. One is kind of handcrafted in using time surfaces at the beginning, and then more like these templates from Ignacio. But we also have in the session the learned spatiotemporal filters to do some saliency. Maybe I kind of missed that, but is Ralph, are you also tracking? So is the saliency used for detection and then you track it, or is all a single model, or do you think you can combine the trackers from Ignacio, or that's completely different, this hypothesis that he's using?
So no, it's completely different in the sense that we are not creating tracks, right? We are basically just saying where is the cluster of events that came in that matched a particular property in the spatial-temporal filters that are sitting up front, right? So there's the HOTS-like temporal surface that basically does the clustering that brings you to a handle, which becomes essentially like, hey, this group of events are moving together, yes, in that sense of a track, but we're not keeping, we're not keeping those relationships, right? We're just basically saying, there it is, there it is, there it is, there it is, right? And now the question is, when us as humans and we're looking at these same cluster of spikes, did we look at them or did we look at something else? Or did we just don't care, right? And can you then do the matching of the two? And there are times when you can kind of very well predict what the humans will look at. And there are times where, it seems like we're looking at little nuances in the background. And those are the things that we're trying to distinguish between the two, in the different events, different filters. Does that make sense?
Thank you. Yeah, thank you.
I mean, maybe I can comment a little, but I think that maybe it's not as far as both approaches seems to be, right? Because at the end of the day, if we think about a method I just proposed, it's also tracking by detection of sort, right? And in your case, it would be more of a classification problem. We started the same with some kind of a classification as, is this matching this class of sort? And we just migrated it to a way that we can transition in an event-based fashion. But in reality, it might not be that far apart, but obviously we need a bridge between the two approaches.
But don't you also provide some form of a vector? I mean, when I think of tracks, I think a vector associated with each, with each centroid, so to speak, right? That basically tells you where it's going. But you do that, right? But we don't, right?
It's implicit. It's somehow implicit, right? If you think of the problem like the continuity of the problem, you can say, okay, this has happened really close, so you suspect that it's going to be the same thing, right? In your case, if you have a cluster and a unique cluster in the image, and you see a unique cluster later on, you are going to assume that it's the same one if it's really close, right? So
right in time. Close in time, close in spatial time, yeah, spatial.
Exactly, and then it's rather implicit. Obviously, we have the vectors and so on, but it might not be as far apart as it seems initially.
Yeah, interesting. Yeah. Anyway, I'll have to pay attention to your paper a little bit more and see how we can bridge it.
Okay, I don't know if there are other questions. So to answer, okay, Coben answered me on the chat. Okay, cool. Okay, and I don't read the answer. I mean, the chat can be followed by people. If there are other, I don't know if there are other questions. Otherwise, we can continue and go on.
No, it wasn't a question. I was just answering your earlier question about scalability of the H tree going to bigger imagers. And, by basically going parallel and pipelining, basically, operating the various levels of the tree concurrently, we can get to some like 0.5 giga event per second with the current, based on our current measurements.
Because in practice, from my experience, what you can have theoretically with a 1 megapixel sensor, you can arrive up to 3 giga event per second if you want. But this has become very, very difficult to use.
Yeah, I think to get there, there's extra tricks, just a whole new generation. But I'm not going to get into that because that's it's very speculative.
It's starting to be very problematic after this.
I like to build stuff before I talk.
Okay, this is good.
One question though, Kwabena.
Yes.
Kwabena, I have a quick question. So in memories, don't they use these kinds of mechanisms to get to really dense memory to route data in and out of it?
A tree?
Yeah, like a way of.
No, they still have row and column lines, right?
Still doing row and columns? I thought
we have no row and column lines, Ralph. None.
I have a question related to representations. I think Stepan is also writing about it. He asks, what should the representation be from the event-based sensor? Should event camera output some higher level representation like BioRetina? And I think what one can see from the work of Ignacio and his PhD and also some previous talks and the school from I guess from France, that people are using time surfaces, but I see that Ignacio is not using time surfaces towards the end of his PhD. There are many trackers that are using these time surfaces, but it seems that now he's moving away from this representation. So maybe we could talk a bit about representation, which is a very interesting topic for computer vision.
I mean, if you want, I can start with that. I think that it's a double-edged sword in the sense that surfaces of the basic type, right? You will have surfaces that just accumulate information and update it. You have time surfaces that decay and so on. They're meant to provide a static representation of what's happening, right? We also propose our own way of sorting it and so on. The things that you need to, we are so used to look for static representations because they were used in CNNs and so on, right? So in that regard, I wanted to be a little bit more free from that because you are taking some assumptions from it, as in how much time do you have to accumulate information, or how much can you rely on this, right? And how you cope with coping with the noise. I think they are necessary at this stage, but I believe that eventually we will evolve from that towards something that comes more natural to the actual event itself, right? Like more to the point cloud and less to the image itself. But that would be only my take here.
So let me also add something to that. Our experience with time surfaces in self-motion sequences like the prophecy or the DSEC or the MBSEC is that this is there really, you can hardly see like a structure unless you have a very strong like noise reduction before that, much stronger than what Toby has done, or some like saliency like the one, I don't know if it was Bernabe, but in the order of like 1% probably reduction, and then you can see something. But if you actually want to learn the time surfaces using some optical flow signal, then you can see them much clearly. But without any supervision, I think for self-motion sequences, it's really very hard to deal with. I don't know if anybody, I mean, I'm asking everybody if they have, if anybody has done something like a time to collision or focus of expansion computation using time services.
Not using time surfaces, no.
So I think it's
graph
really
convolutional networks to segmentation used really the time surfaces over a very long time.
I mean, still you need some reduction of the signal at the beginning. With the 640 by 480 with the new sensors, this is really, you cannot build a graph.
No, you have to downsample.
Yeah.
Maybe there are better techniques, of course, downsampling, yeah. Heavy downsampling before you start.
I think the saliency work is spot on for everything, not just for a salient region, but also for saliencies in XYT.
Right, the time surfaces do carry information about the little time window too, which is characteristic and lets, for occlusions especially, is great, carries information that we can't see instantaneously. When things cross each other, move on top of each other.
It's interesting that now we have moved to these sensors that they can capture edges, and we were thinking that it was sufficient for sparsity, right? And we face the situation now that we are pushing the boundaries so far that the edges are too much information already, and we have to downsample it or summarize it even further, right? But just because we are pushing for higher and higher event rates, right? At the end of the day, I think that it's a fight that, I mean, I think that the work in Saliency is amazing because we are now focusing on what's important from the scene to be processes, right? Maybe in the future, and there are ways on works, we will have to be working on summarization, as in what will look at a stream into something more compact, but represents the same data, right? The same way that we were talking in the past about Gaussian blurs and trying to go to a scale space for normal images.
Yes, that's where I would put it too. You want to explore the events at multiple time scales, not just instantaneously. That's where the surfaces come in.
Okay. I suppose, Guillermo, we have the time to start the break probably now.
No, we will move then to the DSEC competition.
Okay,
We still have 3 minutes.
Okay, so there was another question about for Ignacio from Julia. Have you tried tracking object moving in 3D? Or where can the tracking method deal with occlusion?
So at the moment, the problem is as simple as tracking a patch in the image space, right? Trying to cope a little bit with this kind of dynamics and try to avoid the motion trail of the problem. So can it track a 3D objects? Yes, it can, right? As a patch, at least. Obviously, if it changes the appearance in 2D changes too much, it will not work, right? It could be adapted easily. But and also about the occlusions, well, it will depend, right? But in general, as it is, it cannot do it because you expect that the appearance is not going to change. The same way that a KLP tracker, you cannot handle something that is arbitrarily changing, right? But it doesn't matter in mind if you have a model for this to be projected to 2D, then it should be feasible to do. And regarding the occlusions, well, we have seen already a bunch of works already on graph segmentations, ways to detach things that is in front of the object, and so on. I think that could be a nice extension to the whole thing.
Thanks, Ignacio.
Okay, Guillermo, you have a question for Bernabé?
Yeah, I think Stefan and I had a question. So
Okay,
for
please.
Bernabé, he mentions that sensitivity goes high, but the dynamic range.
The dynamic range, it's intra-scene dynamic range. So you still have the full dynamic range. The sensor still works for low light and very strong sunlight, but not simultaneously on the same scene. Because we had to add some, like in normal cameras, some adaptation mechanism to adapt to light. So for the same scene, you will be limited. It's due to because we introduced diode connected NMOS transistors and the voltage adds, and then the power supply rail will limit. But if we have access to some technology that has like 0 voltage, threshold voltage for the diodes, then this would not be a problem. But that would be a special technology, not a standard CMOS technology.
Thank you. I think there is a follow-up question, right, Davide?
Yes, there was a comment from Toby, I see. And the question is, can this trade-off be controlled somehow? I suppose it's calling about trade-off between the dynamic range and the sensitivity.
Yeah, it is similar problem, yes.
Okay, so I suppose that the panel is finishing now. So we can go with the next.
Yeah, thank you very much to all our speakers in session 2. And now
Yes.
we move on to the results of the competition from Matthias.
Okay, let me share my screen. Can everyone see my screen?
Yes.
Perfect. All right, so I'm going to talk about the DSEC competition that that was hosted by this workshop organized by Davide Scaramuzza and myself. And just to quickly summarize again, the DSEC dataset, we have released it recently in ROL. And it's a dataset with 1 hour of driving data and about 50 sequences, day and night HDR scenes in different environments in Switzerland. And what we've provided so far is disparity/depth ground truth from LiDAR. And in this context, I also want to quickly give you a short outlook of what is new. So we added exact exposure time data per frame of the global shutter cameras. If you want to use that, for example, for deblurring, feel free to do so. Upcoming is a permanent disparity evaluation benchmark, and work in progress is also optical flow ground truth. And planned For the future, yet a bit unknown, is drift-free post-ground truth. That is also asked a lot by others. Okay, so now back to the competition. So the competition task so far was this disparity estimation using events or frames on the rectified left event camera. You can see here, as an example, we have 4 cameras, as you may know, 2 event cameras in the stereo setup of 50 centimeters baseline and global shutter RGB cameras. And you're supposed to predict / estimate disparity. You're free to use either sensor combined. And I'm happy to show that we got 7 submissions, 5 outperforming the baseline that I've trained on the data set, and 2 of them are using stereo frames as well, and all of them, as far as I can tell, are using ANN-based methods. And I'm happy that there are 7 submissions because it was a bit relatively short time. But you can see, for example, that that we have still very good performance. And so, what is the baseline performance that we're talking about? So, DSEC baseline is a stereo matching approach using only events, using voxel grids where we integrate 50 milliseconds of event data. And we use a network that was developed by Stepan Tuliakov, who's actually also listening today. It's actually practical deep stereo, but instead what we use is voxel grids. And that we evaluated on the test set of the DSEC dataset. And so, in fact, all of this baseline of these methods have never seen test data, so there is no way that somebody could cheat in this contest. Okay, so now to the winner. So, hard to tell the name, like Mohammad Mostafawi and Yengwoo Nam from KAIST and GIST in South Korea won the competition using events and frames and have 67% MAE. So MAE is the mean average error of the disparity. So this is disparity error, and they achieved 67% of that compared to the baseline, which is very good. And then the runner-up using only events is Hyakin Kweon. Sorry for the name, I cannot pronounce it. Also from KAIST, using only events, achieving 88.5% of the disparity error. So we're going to have 2 presentations now, 5 minutes each, from the runner-up, which is called CESNet, from Hyakin Kweon, and from the winner, EI Stereo by Mohammad Mostafawi and Yengwoo Nam. So if the runner-up is present, please go on and present for approximately 5 minutes, and then in the end we can have questions.
Hi, can you hear me?
Yes.
Okay, let me just share my screen. Hi, my name is Jae-Suk Jung. I also go by Jason, and today I'll be presenting our work instead of Hyuk-Jun Kwon on spatial temporal event feature extractor for event-based stereo, which has shown the best performance for event only for only using events in this competition. Okay, so first off, we'd like to thank Matthias. Sorry if I'm not pronouncing your name correctly. For creating this data set which has the stereo RGB event data set for driving scenes with ground truth disparity. It's also well all the data is well temporally synchronized through the use of timestamps, and an event rectification map is also provided. So in this work, our goal was to demonstrate dense disparity maps from only using event data. although the data set does provide RGB, stereo RGB image pairs, what we wanted to see is how far can we get with just using stereo event data. So to approach this problem, we split the stereo matching problem into 3 different sections: feature extraction, correspondence search, and disparity regression. And so first, I'd like to note that raw event stream has a completely different modality from that of conventional frame-based images. And what we wanted to do for that reason is that we primarily wanted to focus on the feature extraction portion, which kind of which helps with making up for the different modality. And in regards to correspondence search and disparity regression, we utilize the power of existing stereo matching models that are used in conventional images. So first, we'd like to mention a few event embedding methods, which I'm sure a lot of people in this workshop already know about. So first, we have the voxel, and this event embedding method is kind of part of the whole feature extraction portion. So first, we have the voxel grid representation, where we take the events and stack them temporally into voxel grids. So they would have a 3D shape of width, height, and time. And we can directly input this 3D tensor into conventional stereo matching networks. Next, we also have a queue-based embedding method, where we have a first in, first out queue, and we train a kernel network to convert this queue into event descriptors. So in our proposed work, what we did was we wanted to have an event feature extractor that can take into account of spatial and temporal information. So we decided to use a convolutional LSTM-based LSTM network. So we do believe that there's already various works that use convolutional LSTM to process events. However, we wanted to explore how we could use event voxels in conjunction with convolution LSTM to perform stereo matching. So what we do is we take the event voxel, and then we take each voxel layer and then sequentially put each layer into the convolutional LSTM network. And each of these outputs are then fused together and put into the spatio-temporal event. They are fused together to make the spatio-temporal event feature. And what we do is we take this feature and then put it into conventional stereo matching networks, such as PSMNet. So for our experiment, what we did was we split the training data sets into our own train and validation data set, since we don't have GT disparity for the test set, as Matthias said. So we had 36 scenes for training and 5 scenes for validation. We also made sure that the validation set includes 2 scenes captured in low lighting settings to kind of give some variance to the validation set. Next, for the stereo matching model, what we do is we tested 2 networks that perform well on KITTI dataset, the PSM network and the AA network. But one thing we found out was that the PSM net definitely trains relatively faster than AA net, but still but both of the networks have very similar performance. So in our experiment, we ended up just using PSMNet, and we also keep the hyperparameters consistent as in the original papers. Lastly, we test the various event embedding methods that I've mentioned earlier. So we have the voxel grid representation, queue-based embedding, as well as our proposed spatiotemporal event feature extractor. So here we compare the performance of the different event embedding methods. First, as I mentioned earlier, even when we use the voxel grid representation for the input for both AANet as well as PSMNet, we saw that the mean absolute error was relatively similar. That's why we decided to just stick with PSMNet, because it trains much faster. It trains relatively faster. And so what we did with PSMNet was we tested out the various event embedding methods. So these were the results we got on our own validation set. So in our experiment, the convolutional our proposed method performed better than the others. And then this is the network that we use to submit the test results. And here's some qualitative results on the validation set. And we were able to also generate this error map because we were provided with the ground truth for this validation set, as it was kind of part of the training set originally. So here's a comparison with the baseline network. So baseline output. So here on top we have a scene from the daytime setting where it's driving, or it's a very nice scenery. So what we wanted, so although the baseline differs by around only incrementally, we can see that some parts like the fence are a little bit more refined. Also in the nighttime scene, things such as the poles are also much are more refined. So here I'd like to discuss some of the limitations that we found while working on this. So we only work with events, we definitely notice that events are very sparse in their data format. So that in itself is a limitation, we consider it a limitation. And events are definitely not as rich compared to RGB images. So to emphasize on this point, I wanted to address the photo to the right. So this disparity, this depth prediction result is actually from the night scene image here. But as you can see, the top side, you can see that it should most likely predict sky, which has supposedly infinite depth. But what we see here is that the network itself says that this is very close. So what we believe is that because events don't have as rich of information compared to RGB images, it actually mistakes the light post as tree. That's why it kind of connects the depth from the pole and kind of sees it as a tree. And lastly,
Jason,
we want to, yes.
Jason, can you wrap up? We need to.
Yeah, sure. So lastly, we want to mention that event-only stereo methods are too sensitive to embedding methods, and for possible future works, it'd be good to see some works that have event-adapted stereo matching, cost matching part, as well as disparity regression method. And as some methods suggested in this competition, it's definitely beneficial to use RGB frames alongside events. And thank you.
Thanks, Jason. Muhammad Mustafawi, are you also here?
Hello, yes, I'm here.
Okay. Remember, 5 minutes, we don't have more time.
Sure. So please, Jason, can you stop screen sharing so I could start? Okay, I hope you see my screen. Hello, everybody. I'm Mohammad Mustafavi, and this challenge which we competed in was a work with Young-Woo Nam and my professors, Professor Yoon and Professor Choi from GIST and KAIST. I'd like to thank the CVPR workshop organizers and also the DSEC challenge as well. The name of the method is EI stereo, which we used both events and intensity to predict better depth estimations. Unfortunately, parts of this work is still unpublished, so I will moderately give some details. So please consider that in advance. So as you know, this DSEC and the MVSEC is quite different, specifically what they're focusing on, which is the driving scenes, the scale of the data, which is much larger from the DSEC, and the settings they have, which is different which the grid line of the image and intensity images are different, and they also have different baselines, and they capture much diverse scenes, let's say, in comparison to the MVSEC. And the baseline usually is actually learning an event sequence embedding. That's what they propose most, and their backbone is their previous work from the NeurIPS 18. So in the challenge, what we used is both the events and images. So as the calibration data was available, we warped the images to the event locations, and they nicely followed each other to some extent. And although the image sizes were different, so some part of it might have this loss of the warp, but still good shape. So we used the event representation that we used was the stacking of SPT that was presented in CVPR 19. We presented in CVPR 19. And the problem with the SPT or SPN is that it's dependent on the number of events that we put there. So if you use a lot of events, it will overlap. If we use less events, it might not really follow the APS. So in this setting that we used for the challenge, we used stacking based on time, which we used 0.5 seconds of the event stream and divided it into 3 sections, which each section was taken as an input to our sequential design. So this is the, let's say, general overview of the design, in which we used the events, as I said, divided it into 3 stacks and gave it to our recurrent residual design, which takes events and images together and fuses them as a tensor that could be later on used to estimate the depth with that input tensor. So we also had, we got the first place using events and intensity image, but we also used events only with our approach, and we got the 4th place as well. So by only using events with the similar backbone of the depth estimation. We already know the metrics for the challenge. We got better on all metrics, 1 pixel error, 2 pixel error RMSE, and the main one, mean absolute error. And I just want to tell you that these 2 methods used events plus images, and CES just performed on events. I'll jump to the qualitative results here. So as you could see over here, this is the baseline, and this is our method which only used events, and this is the one that used the combinations of events and intensity images, and it has sharper details and, let's say, more details on different locations in comparison to the other ones. And so problems of events is sometimes if we have a lot of events going on, for example, if a car is driving by, it will consume a lot of the events and the details of that car, specifically for capturing using time, or even if we're capturing based on the number of events. This part will consume much of the events. So some other parts might not be rich as much. So that's why maybe the baseline cannot really capture all of it, although our event only does capture to some extent, but some parts are still require, let's say, the intensity images to be more rich in details.
And Mohammad, consider
Yes.
wrapping up. You're running out of time.
Sure. So these are just some other samples I just wanted to show that the events by themselves cannot really perform nicely as if we have the intensity image as well. We could have much more details on different locations. Yeah, so these are the results. I'll just skip. And the take-home message is that image-only depth is good if we don't have motion blur or repetitive patterns, if we have actually enough details. And event-only is good, but sometimes it misses the details when there's no relative movements or when we have too much movement, which makes an overflow in the stacks. We saw this because we see the different event representations. to get this conclusion. So event intensity depth is more than good, as it could use both events and images, the good parts of both of them, to create better depth values, but it's still challenging and open, and I believe many new methods will come and tackle this problem. So thank you once again. And yeah, that's the end of the presentation.
Thank you very much, Mohammed. And thanks everyone participating in this challenge. And I hope to see more submissions in the future when we set up a permanent evaluation. And also everyone in the workshop, feel free to give some feedback to our dataset or suggestions, what you would like to have. Thank you very much.
Guillermo, are you connected? Okay.
Yeah, I mean, we could have like a 5-minute question and then we could move on to the awards. I will make it shorter. So are there any questions for the winners of the competition? I guess I have a question, is how sensitive is the result with respect to the input representation, how you convert the events into a grid that then you pass to the neural network? I guess you have tried different ways to convert the events into tensors.
So with the amount of time we had, we were only able to test the 3 cases: the voxel representation, the Q embedding method, as well as our convolutional LSTM-based method. What we saw was that the event Q method is the Q stacking, its Q generation itself is a very long, time-consuming process, yet it doesn't generate as much performance as the voxel methods. And just simply using voxels is not enough to extract enough features from them. So that's kind of how we got the idea to add on the extra convolution feature extraction portion to this voxel grid representation.
So I'd like to add, in addition to Jason's talk, that it really also depends on if you're using the different stacking methods based on the time that we had or based on the number of events. So it is relatively sensitive if you use the fixed amount of the events and train on the network, but it generalized better when we try to use the time slots instead.
Then there was a question in the chat from Federico. That's kind of what we are talking about. What is the difference between yours and the 3 consecutive voxel grids? The representation, the input representation. But I think that's more or less settled. There is another one from Stepan. Did you try, Jason, did you try different ways to apply convolutional LSTM? Why did you decide to fuse outputs of the LSTM at different timestamps?
So to answer a question on that, we did actually try we weren't able to try many methods, but the one thing we tried was how we actually convert, kind of stacked up the fuse the different outputs. What we noticed is that instead of fuse giving each of the outputs of the convolutional LSTM the same weight, the last one actually, just simply using the last one did show good performance in terms, and the reason we wanted to fuse, or the initial reason we wanted to fuse the outputs of the LSTM at different timestamps was to kind of give additional temporal information to the network to better predict the depth.
Okay, there are two more questions. I think we could take one of them, for example. For event data for Mohammed, how long is the time span that you stack for every input? Is it the same as the corresponding intensity image?
So what we take as input is the input intensity image and 0.5 seconds before that. And we divide that 0.5 seconds into 3 stacks, which each have 3 bins. So that would be the input and up to the time of that specific intensity image.
Okay, I think the rest of the questions, we could take them offline. Maybe you could answer them. And let's move on. So I want to clarify that there was like a confusion. This award ceremony is not for the competition, it's for the papers. So let me share the screen. Okay. Does it work out? Can you see it?
No, we can't.
Not yet. Strange.
No.
Now? Now?
Yes, now it's working.
Okay. So just like 2 years ago, we had this also like 2 selected papers among all the accepted ones that were presented at the workshop. This year, we also have that. And so here are the bit of recognition for those papers. So first of all, we would like to thank our reviewers. It was a very fast and thorough process. Thank you very much. Without you, it would not be possible to review so many papers in such a short amount of time. I think we had about 28 valid submissions, and out of these 28, we selected 14 that were accepted to the workshop. And nevertheless, the other 14, maybe they were rejected. We still got good feedback from the people who received the review, saying that we do really care about the review process. So thank you very much. And about the committee. So in the committee for the paper award, we had almost the same committee as 2 years ago, in the sense that we have Mike Davis, a very well recognized researcher from Intel Labs, leading the Loihi project. We had also Cornelia, she's a co-organizer, and we could not have Professor Leitenegger because he was busy, but we had Gary Korchar, who is also a very well-respected researcher in the event-based vision community, to judge the different papers. And the awards are sponsored by Prophecy, and may I say that, as a disclaimer, that none of the jury members had any affiliation with the workshop sponsor. And I think Cornelia is around, so maybe Cornelia, would you like to take it from here?
Okay.
Yes, we could go first, the second, the runner-up, and then the first one.
Okay. The runner-up is the paper V2A from video frames to realistic DVS events by Yuhang Hu and our old-timers Shichi Liu and Toby Delbrook. And we like the paper because it provided an accurate simulation model of DVS pixels under low light conditions and demonstrates how training using simulated low light events can improve model performance. Low light operation is often cited as a strength of event-based sensors, and this work provides a valuable simulation and training tool to help the event-based sensing community deliver on this promise. So congratulations. Johan, Shichi, and Toby.
Thank you. Thank you. That's very nice to hear.
Great.
Good, and then you will receive this. We also made like this special kind of poster that you will be able to display same information.
Oh.
All right.
I got a screenshot. Thanks.
Good.
Very
thanks.
lovely certificate. Beautiful certificate.
Congratulations.
everyone.
You contributed again. Give us the camera. Now you told us how to simulate. All right. So then are we moving on to the first prize? So, and the first prize goes to the paper Detecting Stable Key Points from Events through Image Gradient Prediction to Philippe Gibert, Etienne Perrault, Amos Cironi, and Vincent Lepetit. And we like this paper for advancing the state of the art for stable key point tracking with event-based sensors. The approach exploits event-based cameras' intrinsic sensitivity to image gradients and the Harris corner detector's reliance on gradients. By combining the two, you have achieved a key point tracking algorithm which appears both efficient and effective. Maybe it will be used in those stereo and tracking algorithms. So congratulations, Philippe, Etienne, Amos, and Vincent.
Thank you very much.
Here you have the certificate.
Yep, done, thanks.
Good. Well, thanks very much to the jury for the reviewing and judging these papers. It was also in a quite short time. Now we move on, and we have the intermission. So we will have this organization. I know originally it says to go into Gatherly, but I look at it and we have only 20 places in Gatherly, and we have 22 posters or speakers because we have 14 papers and some invited courtesy presentation. So let's stay in the Zoom. I think it's actually easier. So I will create some breakout rooms, but this is basically where you should go. I hope everyone can see the slide. Yes.
But Guillermo, can you just clarify, are we supposed to go to Gatherly now, leave Zoom and go to Gatherly?
No, I won't. I think we don't have enough space in Gatherly. So I will go to Gatherly and tell the other ones to come here, but I will create the breakout rooms here.
Okay.
Okay, so
It's
I
a
will
shame,
create,
right? Yeah.
I will create 22 breakout rooms, and then the number that it's there is where you should go. Okay, they are open.
And how long does this go on?
So according to the schedule, let me go back to the slides. The schedule, we come back at 2 p.m. Eastern time. So we make it a bit shorter because we are a bit late on time.
Okay, about an hour.
Yeah. Okay. So let
Thank you.
show again this one. So I think the rooms are open. If you see the rooms, I think you can assign yourself to the rooms and you can move around. Yes. So room 1 should be, for example, Joey. Room 2 should be Stepan and Daniel Garrick. Room 3 should be Federico, and so on.
Mm-hmm.
The paper should be Toby and 7, and also in 18. Are we good? Okay.
It's all clear. It's clear. Thanks.
you hear me? Okay. Is the library like closed though? Wait, seriously? Where are they gonna? But there's like another library, right? That you can like they're putting all the books in another library, right? So you can still. Did they not plan it? Yeah.
Wow, 7 years. And they have to be a nice preserved place with insurance, right? You need insurance on them. Well, nobody's going to steal a piano, but still the building could burn down. But how much do they cost?
$70,000, genius.
We're unmuted. Wait, sorry. Hold on. That was fun.
Good, thanks. I'm glad you like it. It was a bit of a difficult situation with people in Zoom on Gatherly, but I think we're mostly here on Zoom.
That's cool.
Okay, let me stop sharing the screen.
Come back later. Bye-bye.
Bye. Okay, I think we are going to start now the third session. And this is Cornelia and I, so I could lead it. If it's correctly, we have Julia, then Anthony, not there. Then Guido, and finally Chiara. Okay, Guido's there.
I'm here too.
Julia,
Shall I
yes.
try to share my screen already?
Yes, please. Okay, let me just.
Yes, you give such a nice overview. So hope you can summarize it too.
Let's see. Right. Can you see my screen? Maybe I'll leave it here because we need to summarize, right? So I'll just jump over slides quickly. Thank you very much for inviting me to this workshop, and thanks so much for holding this workshop, which is, I think, a milestone each time it happens for event-based vision and neuromorphic computing. So I thought that by this time at the workshop, someone will already talk about neuromorphic computing hardware and present it, and that didn't really happen, and I think that's telling. Yeah, so event-based vision sensors and neuromorphic computing hardware are kind of siblings. Well, they were born in the same lab. They share the same DNA of event-based spiking representation of signals. And it should be obvious that neuromorphic hardware should enable amazing performance in event-based vision applications. Because there's such a nice match between representations. But it seems that we are not quite there yet. So in this talk, my main goal would be to see where we stand now, what has been tried in neuromorphic hardware, mostly in our Intel's neuromorphic hardware, in our Intel neuromorphic research community in terms of event-based vision, and what is maybe missing, what is the path to the future. To set the scene, there are people call neuromorphic hardware very different things, right? So our Loihi neuromorphic chip is a digital device that simulates spiking neurons. There are a couple researchers here who have developed mixed signal devices, and there's a whole community that builds devices based on new materials like memory assist technology. So to agree, at least for this talk, like what is neuromorphic computing hardware, I would maybe emphasize three components. The first is the neuronal model. And the neuronal model, of course, has spiking character of exchange of signals and information between neurons, similar to event-based camera. So we exchange information with spikes or events. And the second component of the neuronal model is the temporal character of processing. So in each neuron, we have temporal filter on the internal dynamics of the neuron. So activation is not just number, it's number that develops over time. And we also have some temporal filtering on the synapse. And in today's hardware, these temporal filters are fairly simple, right? We have leaky integrating fire inside the neuron. We have some decay usually, or some delay, fixed delay on the synapse. This maybe could be done more in a more complex, more powerful way to increase the power of neuromorphic computing, something that Riyad mentioned that might be needed. So first, the neuronal model. Second, the network topology. So when we think about neuronal networks today, we have this picture, with layers and layers of feed-forward processing, convolutional or fully connected, but usually feed-forward networks. Neuromorphic hardware allows us to wire up whichever network we want, right? We have a bag of neurons, we have connections between them. So the space of algorithms that we could implement in this hardware is immense, right? We can come up with many different structures and implement many different algorithms. The big question that I will try to illuminate in this talk is how to build those algorithms. We have deep learning, but do we have anything else is the question. And the final distinguishing characteristics is learning. So learning in neuromorphic hardware is biologically inspired. In biology, neuronal networks seem to use these local learning rules so that every synapse in the network can change, but this change is only informed about two neurons that the synapse connects and nothing else in the network. So if you have some optimization-based learning technique, you have to make sure that you can break down your learning process to these local learning rules if you want learning to run natively in neuromorphic hardware. So at Intel, we have developed the neuromorphic research chip Loihi. It's not a product, it's a research chip with different form factors. And for this community, the most interesting is probably the smallest one, USB stick form factor device with 200,000 spiking neurons. So you can estimate the size of the networks you can build there, which has a direct address event representation interface with which you can connect event-based sensor to it so that you don't have to go over a computer before you get to actual neuromorphic device. And then we have some larger systems, and there are new systems are being developed. So the big question, what does it take to enable event-based visual processing on neuromorphic hardware, right? So we have our events, and then we have these neurons, they have their internal dynamics, their spikes. How do we let them do something useful? And then this is the full list of methods that I could think of while looking at the work that has been done on Loihi so far. Deep learning is, of course, the first thing people try because it's so powerful in conventional vision. And you can apply deep learning by pre-training your network as a conventional deep network and then converting it in a spiky neural network. You can also do deep learning directly in spiking domain. I mentioned it briefly. You can design spiky neural network-based versions of some other algorithm. Take your favorite optic flow algorithms or some segmentation algorithm, and one could find a spiky neural network version of that or equivalent. And many of these algorithms could be, some old or maybe some completely new algorithms, which we never thought of because we had our conventional computers in front of us that have certain constraints and certain things run faster or slower. So as I mentioned, the space of algorithms is really huge. One can also do direct search of network structures using, for instance, evolutionary optimization, and maybe there will be a talk on this topic in this session as well. So that if the network is not too large, you can probably find an efficient structure that will solve your task just by searching the space of network structures. Or one can just get inspired by biology. In neuroscience, people have discovered many circuits in different animals, often in some small animals like insects, locust motion detector, giant motion detector neuron, or in bees or in flies, have discovered different structures that solve some tasks. And one could port these structures, these algorithms to neuromorphic hardware and by that make them do something useful. I will stop a little bit on this slide and then I'll go through the other ones very quickly. So deep learning in spiky neural networks is the first thing that people try to do because today you don't really want to design those algorithms. You have your data, you want to train something and let the network discover the structure that's needed to solve your task. Well, there are three ways how you can apply deep learning on spiky neural network. The first one is training conventional artificial neural network with a backprop, and then converting it into spiking network, mapping it on Loihi. One can do that. One won't lose much in accuracy if one does that right. Sometimes you have to take constraints of the hardware into account when training the network. That helps. And when people do that, then usually they use so-called rate encoding, so that the values of neuron activation, all those numbers, they will be represented as firing rates of neurons. And you can see how that is not the best way to do things. So first, your neurons then have to fire a lot. They have to fire like crazy if the value is large, and they have to fire once in a while if the value is small. They also won't be the fastest network, again, because you have to sample these different rates. So you have to wait for your slowest rate to emit a spike. But this is the first thing that people try. And it's a bit dangerous to conclude about the power of neuromorphic hardware based on this approach. One can use training directly in spiking domain. What you do there is that you take your temporal structure of the signal very seriously. So your temporal structure of the signal should then matter for your task. Because what in many of these networks, for instance, Slayer, which is training with surrogate gradient, where you train both weights and delays. So your network will be fine-tuned to the particular temporal structure of your signal. And then usually you would use spike timing for representation of information. So it won't be rate of neurons, it will be the special temporal patterns of spikes. And the third thing that you can do is pre-train the network with either of the two ways, and then leave some place for using that on-chip learning, that local plasticity that we have on the chip. And if one does that smartly, then one can develop quite powerful networks. I will just flash the couple examples. Most of you probably know them, right? With Slayer, the first example that has been done is training the network to recognize gestures. the DVS gesture dataset. So I think it's notable to remember here that Slayer learns the spatial temporal structure of this task. So the temporal character of all these events is important and can generalize because, of course, many of the events are noise. One has tried to combine vision with tactile perception and then learn association between the two on chip, again, using online on-chip learning. One has tried to take that pre-trained network for gesture recognition and then make the last layer plastic. So introduce additional output head for the network that will be trained on chip with local plasticity. And so in this paper, it has been shown how a new gesture can be added to the list of the gestures that you had in your data set. And this, of course, needs to respect constraints of the usual continual learning, right? So your second to last layer needs to be representative of this new gesture that will come. It cannot be something completely wild. Now, is deep learning the only thing you can do? And as you might guess, not. So I will show this example here, although it hasn't yet been applied to event-based data, it has been applied to images. But one visual task that can be solved without deep learning, rather be solved with something like k-nearest neighbor search, is the task that we solve when we do place recognition in SLAM. Right? When we travel around the environment, we store different views that we have encountered on the way. And then when we see some view, we want to immediately find a match in a long list of memories that we have stored on the way. So, place recognition. So we have shown in our larger Loihi system, one can solve this type of task very efficiently. And the trick is, so you have your image or you have your event-based representation. You find a way how to efficiently encode it on chip. And here it's efficiently encoded by using first sparse coding. So you use features that allow you to represent your image in sparse vector. And then additionally, you represent this vector in a spatial temporal pattern of spikes. So the values are represented in the timing of spikes. So you have a very compact representation that can be stored efficiently on chip, again, with delays and waits on chip. And you store many such patterns on chip. Do I have not too much time?
Yeah, 1 minute. Yeah. Can you start
1 minute?
Up?
Okay. I'll just show how efficiently this we can make a big jump. So if you have stored 1 million of such images and now you want to recognize a new one, you can immediately stream this new image to the thousands or millions of other images already stored and immediately get the result. So what I show later, continual learning is very important. We can make good use of that plasticity on chip if we enable autonomous learning. And to enable this autonomous learning, we have been designing neuronal state machine that kind of orchestrate processing in the spiky neuronal network, kind of switching between training and learning phase. This just flashes that you need more than just object learning or recognition. Usually in many tasks, like for instance, in the robotic learning task, you also need to control behaviors of the robot. You might want to form some spatial representations. And neuromorphic hardware can help you to have very fast vision for control. So in the end, like one vision could be that you can have full processing done on chip. I will spend maybe 20 seconds on these slides because that's important. You can look for more details in the recent IEEE proceedings paper that we have published. And this paper shows how well different workloads run on Loihi compared to other hardware. And it shows us in terms of energy advantage and solution time advantage, Loihi versus other hardware. And we can see that all those deep learning converted networks that use rate code, they all land somewhere in this corner. So sometimes you have some advantage, but usually not much. And in this corner where you get 5 orders of magnitude advantage in terms of energy and 3 orders of magnitude in terms of time. There we have these other types of algorithms. It's either some recurrent neural networks like controllers or some sparse coding graph-based networks, k-nearest neighbor search, different SLAM algorithms or constraint satisfaction problems. Yeah, the challenges. So develop the algorithms for hardware. Why don't we hear many talks about vision algorithms running on hardware? Because developing algorithms there is a real challenge. Benchmarks, I think, is a challenge for all of us, and all the tools, libraries, software, user interfaces that we are just lacking. And to comment on Riyad's comment, computing hardware is not really set in stone. So I think we are still in this learning phase where we want to learn from trying to use this hardware in different applications, what needs to be changed and adjusted. To go beyond even copying the brain. So I think copying the brain and understanding it better is great, but maybe we can even go beyond. All right. Yeah, listen to the talk for the rest.
Yeah, thank you very much, Julia. That was quite a good summary. Yeah, next one in the line, it's Samsung. So we have Anthony Bisulko and Volkan Isler as representatives.
Yeah, thanks. I'm going to share my screen. Oh,
I hope you can just take over control.
No, I need you to stop sharing at least first.
I did it.
Oh, there we go. Thank you. This screen. Good. Oh.
I have a question for Julia. No, it's too late, or
it's too early, I think.
Okay, okay, I'll keep it for later. Sorry.
Could you write it on the chat too, so that we don't
will
forget?
Absolutely do that. Thank you. Sorry.
Thanks.
All right, now I'll start out then. So hi, my name is Anthony Bisulko. I'm one of the event-based camera researchers at the Samsung AI Center, New York. Today I'm going to be talking a little about high-speed perception action systems with event-based cameras. So going over briefly about the Samsung AI Center and some of the stuff we've been working on. So this is our AI Center in New York City. We're located in the Meatpacking District. In the top left here, you can see our lab space. We have a pretty big lab space. We have motion capture system, a variety of robot platforms, some great views, and great office space to work together. You can see some of the things we're working on and some of the things we're thinking about here in our Samsung CES presentation from 2021, where our President Sebastian Sung goes over some of the things we're thinking about in the future in terms of how we can have robots in possibly kitchen environments help us out with daily tasks such as preparing the dinner table, pouring wine, and a variety of other tasks. So we have a lot of work working on these sort of foundational AI issues, perception issues, lots of different tasks within this. And this is sort of some of the motivations behind our center, and we have research doing various parts of this pipeline. Just going over quickly one project that we've been doing before we go into the event-based rhythm research. This is some of our research on picking and placing and clutter. So you can see here we have a cluttered scene. We're going to pick an object, and from that we're going to pick this up. We've done some novel research in each of these sort of aspects here, from perception to motion planning to the actual action that's occurring here, and tried to put this together into a really nice demo to show you guys. So this is one of our projects. Now jumping into some of our event-based camera research, we're going to jump into one of our first projects, which was near-chip dynamic vision filtering for low bandwidth pedestrian detection. This was done along with some of my great co-authors you can see down here below, some of them in the audience today. So going over the problem there we were interested in, the things we were thinking about, was we wanted to sort of apply DVSs to IoT systems. And one of the things about IoT systems is just the low bandwidth stream you need. If we're thinking about networks such as LoRa or other wireless standards that could have some long-range interface, we need this low bandwidth stream. And if we want to pair DVSs to these low bandwidth networks, we need to think about two things. One, which was coupling this with some basically event stream compression that could basically sparsify our event stream so that we could use this. And then for our example application, we looked at pedestrian detection. So we looked at pairing this compressed event stream with a binary neural network to use the binary events along with binary weights to do very efficient inference on the entire process end to end here. So we invented some algorithms overall to sort of do this near chip. So we'd have basically a little algorithm that is first removing some of the noise in the event stream. You're seeing here a pedestrian walking around. You can see how noisy the event stream is originally. We then sort of do a coincidence detection operation, which removes this first noise, aggregation, which gets us to a normalized thickness of edges, and then a subsampling / coding, since we don't really need the full spatial resolution to do simple tasks like pedestrian detection in our example here. We implement this entire operation onto an FPGA, at least this denoising step and aggregation. You can see some of our steps here going from the event parser to, we show a UART interface here. This could be going onto a LoRa network or anything else that you would want to switch this out for. And then we pair this then with a binary neural network to do pedestrian detection or classification. We ran this on a microcontroller, the actual binary neural network. So in some sense, you would have your event stream compression occurring near chip. This would go off onto some IoT network. we could receive the stream and do inference on this in whatever edge compute you want to have there. So this showed that our filtering module was good for reducing the bandwidth overall in terms of the entire stream here, removing the noise, aggregating edges, subsampling, applying some Huffman coding, was very useful to sort of match these for IoT networks. And then also we were able to increase our testing F1 score in terms of our pedestrian detection performance by doing this denoising. So one of the things we think about in the future is we can integrate this onto possibly a DVS ASIC, improve the compressor performance, or possibly integrate multiple sensors so that we could have a better sort of simulation here on platforms of using multiple DVSs. So this was one of our first sets of work looking at near chip pedestrian detection. Our second set and sort of the main idea of this talk was sort of fast motion understanding and spatial temporal networks and dynamic vision sensors. So we looked at the problem here of trying to do rapid motion estimation in dynamic environments. So this could be a quadcopter, which is in a forest, and you need to avoid debris, or you need to avoid incoming obstacles. This could be in a kitchen environment where we want to understand possibly a chef's motion very fast, or we want to understand the things that are occurring around us to possibly react with a robot arm to do possibly a similar motion. This could be an autonomous driving scenario where we need to avoid incoming obstacles or cars around us. So we looked at this problem of high-speed motion understanding. And the first sort of sensors we can grab out there are active sensors. So sensors that send out some signal into the environment, receive these returns to perceive the environment around us. We're showing you here an example of an Intel RailSense with the right, where we have a flying dart approaching the camera. And just due to the spatial resolution of this sensor, we're not actually able to resolve out the flying dart in this example. But the main point we're trying to show here is the fact that active sensors, they do have some power utilization due to high power utilization due to sending an active signal into the environment. As opposed to a passive sensor, for example, like a DVS, where we can, here in the bottom right, I'm showing the same flying dart approaching the camera, and we're able to track this through time, resolve it out, and afford us these very low energy properties, but also great sampling properties for understanding this motion. So we look to biological motion understanding to sort of draw inspiration to how we actually do this motion understanding. Animals use visual cues to see what they should do in terms of planning escape behavior for a looming obstacle. For example, an object could be increasing in size in your visual field. This produces some looming response, and from this looming response, you want to plan some escape behavior. To model this, we looked at trying to inspect spatial temporal patterns in the event stream so that we could do very efficient avoidance maneuvers. We collected a data set, which you're going to see here, of a toy dart, which is going around 16 to 23 meters per second, approaching our event-based camera. And we looked at trying to perform an avoidance maneuver and trying to understand this motion overall. We also collected a ball data set you can see down here on the bottom. And to actually then try to understand this motion, we tried to model our algorithm in a few steps. So the first step, we acquire our XY polarity and time. We try to encode this to a set of, basically, we're trying to encode the history here of events. And we do this by a set of exponential filters. So you'll see down here on the bottom, these are exponential filters which look over basically a smaller time window. So you'll see very short portions of the motion, as opposed to the filters on the top where you can see the longer trajectory of the dart. And we're hoping that this encodes the various temporal properties of the event stream. And what we want to do next is we want to extract spatial temporal features from the filtered event set using a convolutional neural network. And I'm showing you here an example of some of these spatial temporal features. We then try to extract and estimate the time to collision and collision location in a supervised manner to then figure out, all right, you have 50 milliseconds to avoid an incoming obstacle, and this is the direction you should move. I'm going to show a quick example of now, this is an example of our testing set. So you'll see here in the top left, this is a log polar grid where we estimate the impact location. The red is the predicted location, and the green is the actual location where the dart is going to hit you. The next you're seeing is the incoming dart in the DVS event stream frame. To the top right, you're seeing the filtered probability estimates of the impact location. The bottom left, you're seeing the instantaneous estimates of these probabilities, and then finally the time to collision. Our next step, and one of the big things we looked into this system, was really understanding the latencies of the entire system. So we tried to measure basically when the dart began flying, when the dart actually hit the DVS, and how we did this was we had an LED photocell to measure when it left the, when it started flying, and then when it actually would hit the DVS, it would hit a glass with an accelerometer. So we have a full observability here in terms of when the dart begins flight, when the dart ends flight. We collect some events using our processing scheme here. We have an event-based algorithm, which I'm going to show you in a second. We're just doing simple tracking here. And then we have a motor command to say, move left or move right to avoid the incoming obstacle. So showing you this now happening in real time. This whole motion here is about 150 milliseconds. So we're really looking to push the event-based cameras to understand this fast motion and react to it. Showing you another example of this now in slow motion. So you'll see the DVS is down below. We have a target and we're trying to avoid the incoming dart. So this is, you see the slowed down example here, but again, it's 150 milliseconds, pretty fast motion overall. And we're looking to do these very fast sensing, perception, and action pipelines with event-based cameras. So wrapping up my talk, some of the things we found important in these systems, one was determining the right optics you need for the setting, determining what's your minimum resolution for a dart approaching and what you need there. Another important thing was the action latencies remain a large component of the end-to-end system. And some of the things we're thinking about towards the future is improving our terminal state estimation system, thinking about ways we can do this in a faster manner, evaluating some predictive methods to actually figure out where, for example, an obstacle is going, and then some unsupervised methods for perception. So that's wrapping up a little bit of our talk. We are hiring at the Samsung AI Center, so you can check out some of our job postings online. Thanks again for inviting us to this workshop. And if you have any questions, feel free to check out our talk there, or you can see our email down below. Thanks again.
Thank you very much, Anthony. That was right on time. And our next speaker is Guido de Kroon from TU Delft.
Okay, thank you very much as well for inviting me today. Let me minimize this. I hope you don't see it. And let me get started. So I'm indeed Guido de Kroon. I'm full professor at the MEV lab in TU Delft. And I'm going to talk to you about tiny drones. So the first one you're going to see is one that's going to fly into the screen now. It's the Delphi Nimble. It's a special drone because it flies like fruit flies do, or like any flying insect, by flapping the wings, but also by changing the wing dynamics when making a special agile turn. And we think that these drones can lead to new applications like tracking stock in warehouses or monitoring crop in greenhouse, because they're very safe, very lightweight, and they can actually still fly pretty far. But of course, they have to fly completely by themselves. Now, you may realize that this is very difficult because these drones in general are restricted in terms of size, weight, and power, and these drones even more. So this particular drone has a 33 centimeter wingspan, weighs 29 grams, uses 6 watts to hover, and has a tiny microcontroller on board, an STM32F4 with 192 kilobytes of memory. So that's really not much. And what does that mean for autonomous operation? Well, first, it means that the most successful approach to autonomous navigation, simultaneous localization and mapping is actually out of reach for these kind of drones. So SLAM typically takes around hundreds to thousands of megabytes of memory. And I made it red here, and also the 192 kilobytes, because there's quite a big factor of difference here, and we simply cannot do that. Now, you might say to me, okay, Guido, then get a better processor, right? So let's have a look at that. So this is actually a processor that's considered pretty small form factor, NVIDIA Jetson TX2. It has indeed a lot of computation, actually, 6 cores CPU and 256 core GPU, 8 gigabytes of memory, so that's beautiful. Only it weighs 85 grams, so it's 3 times as heavy as the robot, roughly, and it consumes more power to calculate than we need to fly. So obviously, we cannot just put this processor on there. And this kind of leads to kind of like a grim story, right? So are we just not able to make these drones autonomous? Well, we actually are. And the thing that we do is we draw inspiration from nature. And you can get really a long way with that and still work with microcontrollers, to be honest. Because the nice thing about nature is that evolution has found very elegant solutions to complex problems. And so you typically don't need to calculate that much in order to still succeed in successful behavior. But we do think that if you, in the end, go to high dimensional processing of vision, but even if you think of insects, like all the hairs over their body, then I think we do really need neuromorphic sensing and computing. to make the next step with these small autonomous drones. And yeah, our goal is fully neuromorphic, vision-based autonomous flight. So we want event-based camera, some big spiking net, and then we want the outputs to go to the actuators of the drone. Now, we've been studying this for a large part in the context of optical flow landing. And I'm very grateful to Anthony for the previous talk, because he already showed that when this eagle goes down, you know, things get bigger in the image, and there's this divergent optical flow. And that's exactly what honeybees use when landing on a flower. And they do this, yeah, really perfectly, even if there is like wind and things do this very well. And I would like our drones to be able to do the same. And their strategy, like I said, is very elegant. And so let me explain it in the context of a drone. You have a drone, it looks down. If it goes down, then things get bigger in the image, and you have this divergent optical flow field. And if you calculate this mathematical quantity of the optical flow field, the divergence, it actually corresponds to the vertical velocity divided by the height. And these honeybees keep that constant. Now that means that if you're at 10 meters at 2 meters per second, at 5 meters, you'll be going at 1 meter per second, and at 1 meter with 20 centimeters per second. And all of this without additional sensors like we engineers would put, like sonar or radar or LiDAR. The honeybee doesn't need this. And so we did this first with completely traditional elements like a normal camera, normal vision algorithms. But over the years, we've been introducing neuromorphic elements. Now, the first thing that we introduced was the event-based camera. So this, for us, is a pretty big drone, actually, because it had to carry this camera. And you see it on the left is going to make a divergence is one landing. And it's really pretty fast, because all along the trajectory, it's always 1 second away from landing. And you see it in slow motion. On the right, you see the events. So the on and off events in green and red. In yellow, we used the local plane fitting algorithm for the optical flow, which we had to make much more efficient to run on board. Then we extract optical flow. And this was actually the first time that a flying drone was using the event-based camera in the control loop. And immediately it allowed us to do these really fast optical flow landings. So that is very promising, I think, for very fast control of drones. As I said, we were using local plane fitting to do the optical flow determination. But we want, of course, to do this in a spiking fashion as well. And this is what we did next. So we made a spiking neural network that you see here. The input is the raw events, and the output is actually neurons that fire for certain global flow field patterns. So we're moving to the right or the left with a certain velocity or down, etc. The cool thing is this network learns by itself to extract this optical flow. And it does so in different steps. So the first layer learns textural features. The middle layer learns local optical flow, and the output layer learns these global flow field properties, all with the same learning rule. It's a modified version of STDP, which we developed for this study, and we had to develop because of the event-based inputs. And the differences, why do they learn different things? It's all because of structural aspects of the network. So clearly here is like a pooling layer and a dense connection, so it learns these global flow field properties. But the reason that it learns local optical flow is that we introduced different time delays between these two layers here, and then it learns these different local flow patterns. So let us look at the results. So on the left, the inputs, and here, textural layer starting to learn these textural features just by presenting it with event-based inputs. This is this unsupervised learning. So, and then in this MS-conv layer, you see that it learned local optical flow. So this is the rotating disk sequence. Here we have the events. Here we have a color coding for the different textural features. And here we have the optical flow, the local optical flow that comes out of it. Now the final layer indeed developed these neurons that fire for these global flow field properties. Here you see what happens if we move to the left and the right at different optical flow magnitudes. This fourth neuron is active when it's really fast. And then these are active less fast to the left, here to the right. These neurons are silent because they actually specialized for vertical motion in this case. Now, the next step, of course, the control We also did in a traditional way, and we also wanted to do that in a spiking neural network. And actually, we implemented this in the Intel Loihi neuromorphic chip that Julia was talking about, so that they developed. So we're very happy that we could use it. The drone does vision, it determines divergence, it encodes this in spikes, it goes into this chip, and then spikes come out that encode for the thrust that the robot should use for landing. In this case, we evolved the spiking neural network in simulation and then transfer it to reality. The divergence is encoded similar to how our spiking neural network would do it. The output are spikes for the thrust, which is decoded and then executed by a low-level controller to cross the reality gap. Furthermore, to cross the reality gap, we made the neural network as similar to the Loihi chip as possible. And finally, there's some things that you cannot foresee, like the initial height or velocity, delay or jitter in the sensor or USB key or whatever. This was randomized during evolution so that the solution would be robust to these changes. And this is the video. So the drone still looks a bit big because we needed this upboard to communicate with a chip. But I think in future versions, you will be seeing it getting much smaller. And here is the optical flow landing. So this is a direct transfer from simulation to reality. So I must say, yeah, we're actually quite proud how well it landed. And this was actually the first time that the free flying drone was using the Loihi chip in the control loop as well. Now, to conclude my talk, yeah, I think that neuromorphic sensing and processing is a huge promise for insect-inspired autonomous flight of tiny drones. Of course, we're not there yet, so we want this fully neuromorphic pipeline. We want to improve learning mechanisms for spiking neural networks, and we want to tackle increasingly complex tasks. Because yeah, I didn't say that, so I said that we think it's important for like high-dimensional processing. I also think if you look at the repertoire of behaviors of insects, we're not close to that yet at all as well. So we also want to do that. These are the researchers that were involved in the neuromorphic work. And I thank you for your attention. I hope I'm kind of in time and I'll answer your questions in the chat.
Thank you very much, Guido. Very interesting. And now to conclude this session on perception and action, we have Chiara Bartolozzi from IIT.
Hi, do you see my screen?
Yes, we can see it.
Okay, good. So thanks a lot. It's a very interesting workshop, and I'm really happy that I can share some of the work that we have been doing with event-driven sensors. And what I think we learned with this workshop is that there are really many things happening, really a lot of different flavors on how to use event-driven sensors. Sorry, this is going. And so I'm going to show you what we did, and the message basically of this talk is there are a lot of things to do and a lot of different ways to do things. We need to find what is the best approach, and so we are looking at very different ways of using events. So the context of our work is humanoid robotics, and this is the scenario. Basically, we want to have autonomous agents, and the point is that they act in a very dynamic and unconstrained environment. So they have to interact with things that are moving. They are moving themselves, and it's nothing is fixed. We cannot put any constraint in how they can work. So what we want to do is to exploit the efficient information encoding of
Chiara, we lost you.
the sensors.
Chiara,
So the
Chiara, I
use
think,
is the
sorry,
Neuromorphic ICAP. This is a platform for doing yes?
I think we lost 1 minute. At least I did. I don't know.
Ah, okay. Yeah, I just got a message that my internet connection is unstable.
Okay.
So.
Sorry to interrupt.
Yeah, no worries. Actually, this is the timing here in my presentation, so it's going by itself. It's kind of an autonomous presentation now. So I don't know what you heard, but basically the idea is we are in an unconstrained environment and we have to interact with dynamic objects. So event cameras might give us some advantage. And the platform that we use is the Neuromorphic ICAP. So we integrated the ATIS sensors in the eyes of the robot. And so we have binocular event-driven vision. And now we also have frame-based sensors. So in case you are interested, we can also start integrating frames and events. At the same time, we have integrated different computational substrates that we can use to do this computation. So either using laptops or using FPGAs, and also event-driven computational platforms. Giulia, te ne puoi andare, please? Sorry, I was interrupted. I'm at home and things happen. So what can we do with event-driven vision on the iCub? Well, first of all, we can decide if there's anything interesting in the field of view. And this has been presented already by Ralph very nicely. So to me, the job is easier. Attention is a way that biology uses to select interesting regions of the field of view and process them sequentially. So it's a way to improve the computational load. Another thing that we can do is to do feature detection. This is not very biologically inspired, maybe, but it's very much used in computer vision, where we detect features that then can be used for further processing. So, for example, we can detect corners and use these corners for doing stereo matching or for doing tracking and estimating motion in a point that is highly informative and can solve the aperture problem. We can then track things that we have detected. And in this case, we can really use the notion of the continuity over space of the event stream. So if an object moves from one pixel to the other, you immediately see the events moving from one pixel to the other. So it's continuous over space. And then what can we do with tracked objects? We can predict where they are going to be. And this is very interesting in robotics, because once you have, you're tracking something, you can predict where it goes, then you have time to plan the action for the robot and execute the action. So I'm kind of going to go very briefly through these examples, and I don't really have the time, but anyways, you can stop me whenever I don't have any more time. For the attention model, similarly to Ralph, we have been collaborating with Ansfried Niebuhr, and we use the concept of the proto-object model and the depth information. This is because a robot might be interested in something that could be an object, and that is close to the robot, so that the robot can interact with this object. So this is our implementation of the proto-object model using disparity, so as an information that is related to that. That comes from the work of the group of Ernst. And in this case, we, instead of using RGBD images, we use the events from the left and the right cameras on the robot. And to do so, we first create a disparity map using a cooperative stereo matching model that basically helps in computing the disparity in the image and removing the false correspondences of events that have to be matched between right and left cameras. And then we use the concept that Ralph has explained of the border ownership and grouping to detect proto-objects in the disparity map using the von Mises filters. So this is the result running on the robot. We have, well, Julia, that is, moving her hands in front of iCub, and that these hands, they switch disparity depth, basically. You have the stereo events, the resulting disparity map, where you can see that the color of the events changing depending on how close they are to the viewer, to the robot, and the corresponding saliency map, where you can see that the maximum, that is the red dot, shifts from one hand to the other when shifting to the closest hand. And this is what you can see here. The x coordinate of the maximum of the saliency map switches between the location of the right hand and the location of the left hand. And this is when the robot is not moving. But if we want to have the robot being able to perceive static objects, then we start wiggling the eyes so that we can also see the background events. And here you can see that the system is pretty stable. You only have peaks here in between that correspond actually to the face that of Julia, because when the robot moves, also the face of Julia is perceived by the cameras, and it really looks like a proto object. So this is a way to use the sensors that is close to how biology works, and being fully event-based, we can, and we are, implementing this model on neuromorphic hardware. So the next thing I'm going to talk about is this more computer vision type of experiment, where we look at corners. So many different corner detection algorithms have been proposed in the literature that want to run online. With the new cameras, this is very difficult because the number of events that you get is increasing a lot. And so we need to find a way to have an online system that nevertheless doesn't sacrifice accuracy. So what you see here is the kind of the basic infrastructure or structure of the algorithms that were proposed for the corner detection. So basically you have the event stream, and for every event that you get, a data representation is computed. In this example, for example, that is the E. Harris corner detector. Basically, you have a small patch of an image where that is updated every time you get an event. And then there is a convolution with a Sobel operator, the computation of the Harris score, the application of a threshold that then decides, is there a corner or not? Is that an event belonging to a corner or not? And then you have the corner stream. This is completely asynchronous, it's event by event. But the problem is that the time of the computation depends on the number of events. And if you increase the throughput of events, then the system doesn't fulfill the real-time operation anymore. Different algorithms have been proposed to improve this. And basically, they act on improving the data representation and improving the algorithm by trading off accuracy to have something that runs faster. But it's still a lot depending on the number of events. So what we propose is to change the way the algorithm runs, decoupling the data representation update from the algorithm. So we have basically a data representation that is called the threshold ordinal surface that is very fast update for each event that comes. For each event that arrives, you put maximum in this image and you decrease the value of the neighbors, and then with thresholds. So whatever is far in time is goes to 0. And then the algorithm runs as fast as possible. It's simply an OpenCV call that runs on this novel data representation. And it runs as fast as possible on the most up-to-date representation of the data. And the output is a lookup table that gives the Harris score that is queried every time an event arrives. So basically, you still have a corner stream, you still have an asynchronous readout, but by decoupling the algorithm from the data representation, the algorithm can run as fast as possible, and it doesn't create delays in the pipeline, or the delays are very small. So here you see a video that compares our proposal with ARC and FAST. And if you see that, and this is with the new ARTIST camera, and you see that when the instantaneous firing rate increases, ARC and FAST they have very high delays, and you see that they are not synchronous anymore with the input events, while the LUV harness corner are still synchronous with the input. So this is kind of telling us that depending on the data representation that we use, we can improve how fast the algorithm can run. So I'm not going to touch on.
I think we are running out of time. Yeah, Kara.
Okay, I'm just going to the last slide. Let me skip this. Okay, so the message I wanted to give you here was we can have very different ways of computing with events, but the story is not just restricted to vision and computation. There are other things that we can do with event-driven sensing. For example, with using auditory sensing that can be used, for example, for sound source localization, auditory attention, and audiovisual speech detection and speech recognition. It's also very important to use tactile sensors because touch is really localized in space and time. And so the message here is it's really an exciting framework, and vision is, you know, moving very fast, but there are really a lot of interesting things that we can do. I'm done.
Thank you very much. Okay, now we are open to the questions. I think some of you are already answering the questions in the chat. Julia, about one-shot learning. So let me go for one of the questions that it's not answered yet. Chiara, what is the main motivation for using event camera instead of frame camera for attention? And how do you plan to use these attention maps?
Right. There are different motivations. First of all, as I said, the use of event cameras is more general, right? We want to try to use the low latency and have a system that runs very fast. For example, in our scenario, we have the eyes of the robot that can move. And we can have events and frames, and we use a system where we have a beam splitter with event-driven cameras and frame-based cameras that have very, very high resolution, and they are RGB. So what we want to do is have a very low latency, real-time attention system that gives you a region of interest. Saccade to that region of interest and foveate, you know, using the concept of fovea. And then we can use a crop of the proto-object that we have on the RGB and the event to have object recognition, for example, or to have a better perception of the specific object we want to interact with. And this is one motivation. The other motivation comes from my passion of looking at biologically inspired computing. And when you see these models inspired on how the brain works and that they take RGB images as input, well, if we have an input that is more similar to the output of the retina, even if it's loosely inspired on retina, it makes a bit more sense and we can learn something more. For example, one thing that we learned was that, well, the event-driven sensors, they already do edge detection, so you don't have to do that in the model. You can simply skip that because you already have the edges. So you can avoid the center surround, for example, computation there. I guess I already answered to the how do you plan to use this attention?
Yeah, it's good. Thanks. More questions?
Okay. So maybe let me raise some panel questions since we have a few minutes to all of you. Where do you see the greatest impact of neuromorphic computing with spiking hardware in the near future? And especially, where do you see the advantages of these spiking neural networks also in task performance?
I could answer that from my perspective. So I personally believe that robotics is one domain where neuromorphic computing is very promising. And one maybe superficial argument is that spiky neural networks have evolved in biology in order to control movement in real world dynamic environments. So we definitely have something to learn from that. And as robotic systems move to real world environments where they deal with a similar problem and they have to control movement safely, in an adaptive way, control soft actuators. I think these type of networks that are sparse, efficient, but at the same time powerful in terms of representation, and that can be updated on the fly, they can really bring large advantages. Another domain where we see interesting good results is optimization. So if you think, we just have seen some good numbers in application to constraint optimization problems. And if you think of that, many problems that the brain is solving are kind of like constraint optimization problems, right? You want to optimize your behavior, you can have some cost functions that determining how you solve your problems. You have different constraints. They can be just physical, dynamical, mechanical constraints. Your current environment sets some constraints. And then, so we found these spiky neural networks, they solve these problems by exploring the dynamics stochastically. And we find huge advantages compared to conventional hardware. So these are, from my personal perspective, don't take it as Intel's opinion. We explore all kinds of applications. But these are the two.
That's very interesting. So you have specific examples. I know the lasso algorithm, I think.
Or Sudoku constrain satisfaction problems that are discrete, with discrete state space and binary constraints. This is the example that we have has been shown in Manchester lab actually first, and then the postdoc joined us as well. And you just see the scalability is nice. And you can see how that happens, right? We can, like in this massively parallel well, sample the state space efficiently instead of going through possible states sequentially.
I would like to ask
If I may add to this question, sorry to interrupt. I think I can add a couple of things. One is what Bernabe has mentioned, that is the pseudo-simultaneous computation, right? If you have a system that can give you very quickly the output as soon as you integrate enough information, that's very useful in robotics and in any system that has to react in real time. And the other thing that we have not touched, because we are not there yet probably, is adaptation and the possibility to have systems that run continuously, that can learn continuously, and that can adapt to different environments, to different situations. This is, I think, one of the main driving forces that basically motivates us to try to use neuromorphic hardware and spiky neural networks.
I wanted to ask in this session, so all of you have a practical experience in joining perception and action with neuromorphic hardware. So what are the difficulties and the challenges there? I mean, Julia defined the chip as a research chip, not a product. So I guess that's a bit.
I could.
I think Guido can say even more, but I can also
say something about it. So, what Julia also said is that currently, for example, so like I said in my talk, so we do see that in perception, and processing of high-dimensional visual inputs, it would be nice. The current chips, though, don't have that many neurons and connections yet. This is improving as we speak, right, Julia? So that's positive news.
Yeah.
And the second thing is, because it's not a product yet, in order to use it, it's not easy, of course. So that's why, for example, Intel within the INRC, they're working with many parties together to try and start using these chips. And then hopefully when it is a product, it will be easy to use. But currently that's a challenge. And I think connecting a little bit to the last question, you saw the drone that was doing the optical flow landings in the end was actually pretty big for our standard. And that's because from a system perspective, just to interface with the chip, we still needed, for example, this upboard. So I think also there, and this progress is being made, by the way, but in order to be really useful, it really needs to deliver this energy efficiency also from a system perspective. and that we're not there yet, but actually we're betting that parties like Intel and others are going to get there. And so, yeah, so these are some of the difficulties. And to connect to what Chiara said, the learning aspect. So learning these networks, I hear that, you know, yeah, the temporal processing is important in spiking networks, but yeah, personally, I didn't really see this yet, you know, evidence that this has worked better really in spiking nets, to be honest. But please correct me. There's the big experts in the field are here today, so put it in the chat if you want. But I think we really have a long way to go in terms of learning and actually exploiting that those temporal properties of the spiking nets.
Yeah, adding on to some of the points he was making, I definitely agree. One of the big things with these perception action systems in terms of latency and also realizing the power utilization benefits is the glue between all of these things. It's going between an event-based camera over a USB interface to some CPU to do something. It's really the tight integration of trying to put these things together that we've at least noticed does make a difference in terms of your USB latency might be something like 4 milliseconds. So if that's in the end, you are looking at this fast motion applications, that may be important for you. Also, to realize the power utilization benefits, it's also important that a lot of the energy is spent sending a lot of this data off chip. If we actually want to save the energy we have, we need to figure out what are the actual algorithms near chip that we need to run that are important and that can possibly summarize or make our data intelligible for perception later on, or just send it straight to planning and acting. It's definitely an open area of research and definitely a very exciting area at the moment.
I think from my perspective, everything has been said, right? So I can only summarize, right? Systems and input output is important. Throughput, how can we get the data on chip and read it out quickly with low latency and then high throughput? Algorithms, starting with signal representation, how to efficiently represent signals with this threshold-based sampling, event-based sampling. There are some challenges, right, in terms of signal representation or signal sampling. What does it mean that the signal is now sampled in this particular way? So I think some theory needs to be developed there. And then simply, algorithms, how to solve different problems, the neural network, where to come up with structures, how to use learning, but online learning. If we have this online learning and adaptation, many challenges arise, right? Keeping system stable and robust, how to control the learning process becomes a challenge in its own sake. Seeing what is happening on chip, I think, is a challenge, right? Because the chips are usually not built for you to easily access every value. If you do that, you'll slow down the whole system. But for debugging, for development, for understanding what is happening on chip, that's important. And that goes into many practical challenges, the software frameworks, tools to use, so how easy it is to develop a network and then the whole system and debug it, see what's happening where. Yeah, these are probably the main challenges.
Thank you. Yes, I think there are still many challenges and like a long way ahead, and that's good news, good things to do research, right? I think Julia mentions one, or I think in the video somebody, Riyad also mentioned in his video, I think that you have to also train the new generations of engineers to be more like a mixture of engineer and neuroscientists to be able to design those new algorithms, right? It's always difficult to program this neuromorphic hardware.
Yeah. Yeah, so very often so people might just lack some, because you need to be an expert in computer vision, machine learning, deeply understanding the math, neurobiology, systems engineering, design, robotics. Yeah, that's challenging, and ideally have deep knowledge in every field.
One last question before we move on to the next session, if I may, is if you are able to tell us about the roadmap, when will this change from being a research chip into a product that, we can buy event cameras, but we cannot buy neuromorphic hardware yet?
You cannot. So I will,
well, at least not the Loihi, right?
Sorry. Yeah. So it's a research chip. Everyone here can use our chip, right? You just have to join our Intel neuromorphic research community. That was one slide that I tried to flash. So the neuromorphic chips, they tend to be expensive today. right? So, and there's some fundamental reasons why they're expensive. So this cool feature that memory is collocated with processing makes the systems expensive. So this type of memory is just not very cheap. So you can imagine the applications where we will see them are probably not consumer applications where you will have like billion devices sold very soon. So that would be either some very high-end applications where people are ready to pay a lot of money for exotic hardware and also going through the pain of fine-tuning them. This is where maybe Intel could be interested in some products. Otherwise, there could be some niche applications here and there where you don't sell a million or a billion of devices. And there probably small companies have bigger chances to bring devices on the market because they will be happy if they sell I don't know, 100,000 of their devices. Intel probably won't be that happy if that's only that number. So we at Intel, we depend on large scaling up of this technology, that we will find some application where the advantages are so huge compared to conventional technology that, wow, that's very, very promising. But smaller companies and startups, of which there's plenty right around them, they have maybe a better chance to bring this hardware, over the threshold of being a product. Yeah, and we need help, right, from everyone in the community, helping to, at least detect what is missing, right? So if people are not using, if there is a clear formulation of what is missing, then one can act on it. If it's just dismissed, then it's more difficult to act on it.
Good. Well, thank you very much. Thank you to all our speakers in the third session. And now we move on to the fourth one, which is led by Kostas Stanlidis. I think you're muted, Kostas.
This is super exciting that we can present 4 great industrial talks. I start by introducing Luca Vere. Luca received his Master of Science at the Politecnico di Milano and the École Centrale, and an MBA from INSEAD. He did research on Imperial, and after working at Schneider Electric, he took the CEO-ship of Prophecy, where he's also a co-founder. And in many of the talks today, and there are Prophecy chips used, and we were very happy actually to receive recently 2 of them and work with them. We are very excited to listen to all the newest developments. Luca, go ahead.
Thank you, Kostas. Hello, everyone. So I'm supposed to talk 10 minutes, right? Can I share my screen, actually? Is it okay, or?
Yeah, sure.
Okay, perfect. Hold on, let me share my screen. Fantastic. Do you see my screen?
Yes.
Okay. First of all, I'm very excited to be part of this conference, and hello everyone. I see a lot of familiar names, and is actually for me is the first time to join personally CVPR. So and it's a great honor. So at Prophecy, essentially our mission has been since the beginning to bring event-based technology out of the lab to the market. So we believe at the tipping point of this technology paradigm shift and make this technology a real economic innovation. So maybe I will start with some market considerations, and I'm relying on some work that has been done recently by YOL Development, which is a market research firm. So I'm showing some recent results that YOL has been publishing actually in a Neuromorphic report. They refer actually to neuromorphic AI or event-based AI, and we are talking about, they're talking about a $20 billion market opportunity in the next decade, which will penetrate 20% of the global edge AI market opportunity. Here they both consider vision and processing, computing. Then if we move to the vision part, which is the area where Prophecy is active, so when we consider neuromorphic vision only, then we are talking about an opportunity which is about 30–40% of the global the global neuromorphic AI opportunity. And which is also, if you put this in perspective of the global CIS market, the global frame-based image sensor market, it has been estimated that the neuromorphic vision technology will penetrate almost 10% of the global image sensor market by 2030. So this estimation has been made by Yole, but also actually confirmed by a couple of other market research analysts recently. And then when you see actually the breakdown of the segment that they will adopt the technology, you see mobile is being actually the main segment with more than 60% of the market share, but actually not the first one. Industrial is being estimated as the first market to adopt the technology, followed by surveillance, IoT, robotics, mobile, and later on also automotive. And as I said, it's not only about Yole. Many other market research firms and analysts are now acknowledging more and more the fact that event-based technology, neuromorphic technology is becoming a commercial reality. It's not only about research in institutes and universities, academia, etc., but also becoming a real commercial reality. So now transitioning more to what we do at Prophecy, and then talking more about our application. So at Prophecy, we do two things. On one side, we design, implement event-based sensor to fully unlock this event-based market opportunity. And on the other side, we develop also the software. So the software development kit, including a number of computer vision machine learning algorithm that we provide to our customer or ecosystem partners to build the entire event-based application. In addition to the sensor and the software, we actually provide a number of, let's call it development tools, which are, for example, evaluation kit, evaluation camera, which some of you are actually purchased, development kit. So we also provide essentially sensor integrated with embedded platforms such as Xilinx or, for instance, NXP and some others, and also camera module design reference kit, right? So in order actually to really facilitate, it was mentioned actually before, one of the challenges of adopting the technology is really make sure that you can then integrate easily this technology. So we are taking all this burden to also give to the ecosystem, to the market, all the tools that can make the life of whoever is going to adopt this technology as simple as possible. Looking now more at our sensor lineup, so we have implemented so far 4 generations of the sensor. So generation 3 is a VGA. It is in mass production, and this is being currently deployed commercially in industrial automation and machine vision applications. Generation 4 is actually an HD sensor, and it has been co-developed by Prophecy together with Sony Semiconductor Solutions. And it's today at the test sample stage. It is available through our recently launched evaluation kit V2, version 2. And this is actually a great step forward for the sensor development, because we have been using a very advanced technology process that Sony made available, which is a BSI 3D stack process, which is the way to go for this technology clearly, because now we can essentially embed all this intelligence of the event-based sensor in the CMOS layer and then stacking it underneath the photodiode, which of course will lead to a much smaller pixel pitch. So from generation 3, we moved from 15 micron pixel pitch down to 4.86, so almost 10 times reduction of silicon surface, plus all the benefit of a very optimized process, fill factor exceeding 80%, et cetera, et cetera. So we think that now with Gen 4, we are really, we have the state-of-the-art of event-based sensor. And this collaboration with Sony has been announced actually last year at ISCCC. Gen 4 is not only the smallest pixel pitch event sensor, it's also the one with the highest HDR. And this, to me, really the result of a very strong and successful collaboration between between Prophecy and Sony. So we are very glad of this collaboration with actually the market leader, of course, of the conventional image sensor, with almost 50% or even more of the market share in conventional image sensors. So they were very, very helpful in working with us and bring event-based technology to this stage of development. Now, we want also, so the sensor is one part of the story. As I said, the other part of the story is about the software. So we actually started releasing our MetaVision software development kit end of last year. Since then, actually, we have been releasing, updating with a few releases. And today, MetaVision contains a number of tools and algorithms, so more than 95 libraries, to be more specific, of computer vision and machine learning, 67 code samples, 11 ready-to-use applications, mostly for now in the IoT and the industrial automation space. I will come back to this later. All these code samples, application libraries are part of 6 module families, which are machine learning, analytics, calibration, 3D, computer vision, plus other core functionalities. Plus, we have also released recently an OpenEB, so an open source architecture, because we want to enable as much as possible the community of users to adopt the technology. We have, since we released actually OpenEB, which was 2 months ago, we have by now more than 250 active users working on OpenEB. So that's actually great. It shows clearly the interest. And many examples, many of usages of MetaVision SDK. So clearly, and a lot of this actually in real life application with customer. And by now, more than 1,000 companies actually downloading MetaVision intelligence from our website since the launch in October last year. So I'm showing this number because I want to give a sense of how strong is the traction around the industrial interest for event-based technologies. So all these are companies, public, private companies that are currently working with MetaVision intelligence, experimenting, inventing, some actually deploying commercially this technology. So the ecosystem is growing, and that's exciting because, of course, when you come with a disruptive technology, when it comes, comes together with the word disrupting is that you start disrupting also the value chain. So you need also to make sure that the established players in the value chain, they find their own position. So today we are glad that companies like, for example, Sony, Intel, Bosch, Renault, Nissan, for example, they are working with us, they work with our technology to actually cover some of the gaps of the value chain, because we come with a sensor, we come with the software, but you need to put together a camera module, a camera system, an entire solution, a distribution channel in order to really to make sure that from the development to the customer, you have a full, a complete end-to-end offer. And for example, for our generation 3, we have collaborated with 2 companies, one in Japan, CenturyArcs, one in Germany, Imago. They have both developed industrial automation cameras. So these are currently deployed in industrial machineries or industrial processes for a machine vision type of application. So these are applications that are related to quality control and inspection, typically, right? So this is the world of typically high-speed machine vision in real time for some quality control process. I will show you some examples in a second. And we are preparing, as I said, the next generation of the sensor. So we have recently launched our AVK V2, which is running the HD test sample, which was co-developed with Sony. Now, going to, for me, the most interesting part of this summary I'm giving to you. So I would like to walk you through a few applications. Some actually are public. We have recently disclosed our collaboration with key partners. Some other are still undisclosed. So hopefully we will be able to disclose soon. So recently we have announced a collaboration with Xperi for actually the world's first in-cabin monitoring system. So this is typically used for autonomous driving or driving assistance applications. So you have a camera observing the status of the driver for safety-related, of course, issues. And we are running here an event-based sensor, the generation 4, the HD sensor. So in this video, we are showing we can perform face detection and tracking, gaze tracking, head pose estimation, plus some other driver monitoring features like eye blinking rate, eye blinking duration, which are typically used for drowsiness detection and attention monitoring. This video actually has two sequences. I don't know if you observed, but in the first part, actually, the person is running the demo at 100 lux, so typically in an indoor environment. And then in the second session, actually switch on off the lights, showing with a luxometer that we are at below, almost below 100 millilux. And we are not using any infrared projector here, just to show that actually the technology performs very well in extremely low light, and still performing nicely for example, gaze tracking, eye blinking, etc. So this is one first successful implementation, which we are currently pushing to the marketplace, to the tier 1s, OEMs, also last miles delivery robots. And then one other partnership we are announced recently, still in the automotive space, with Terranet, a Swedish public company. They have actually implemented the first event-based LiDAR for automotive. They're using actually three event-based camera combined with a laser scanner. And what they do is that they do some triangulation to following basically the tip of the laser beam. And from that, they can actually produce a very fast millisecond latency level 3D voxel flow for, of course, driving assistance or autonomous driving features. Another recent announcement we have done is with Cambridge Consultant, UK-based company. So it is in the medical field. So Cambridge Consultant has used our technology for essentially produce the next generation of cell therapy diagnostic tool for real-time sterility testing. As you can see in the video, we can detect the cells observed by the camera. And typically this is a process that is quite manual. It takes sometimes, 1 or 2 weeks, so which is quite lengthy and also dangerous in some life critical situation. So we have shown that using an event-based sensor can actually shorten this time for the sterility testing system from weeks actually down to milliseconds. So you can almost perform real-time diagnostics with an event-based sensor. So that's currently being deployed with some medical device companies. And also very recently, a few days ago, we announced our collaboration with Gensight. We are still in the medical field. So Gensight has used our technology for vision restoration of blind using optogenetic therapy. So they're using our sensor. Our sensor is connected to a projector. Project light in retina of people who have a late stage of retinitis pigmentosa, who are becoming completely blind, and they're able to restore partially their vision capabilities using the event-based sensor as an input. So that's actually very valuable implementation of the technology. And now moving to more other recent applications, but which we cannot disclose yet our partnership. We are working actively on live deblurring. Blur is an issue with conventional frame-based technology because when the target moves during the exposure time, typically generates some blur. Event-based sensors don't have this problem due to the fact that they have this synchronous per pixel exposure. So we typically don't have motion blur. So we can actually, by combining side by side an event-based sensor, frame-based sensor, we can use event-based data fusing with the frame stream and correct the motion blur. So the result is what you see in this video. On the left side is the raw video of a frame-based sensor. We are using this exactly what you see on the left and fusing with the event data of a camera, which is again in a dual camera module synchronized and calibrated together with the frame-based sensor in order to correct the motion blur. As you can see, actually, in some of the frames in the end here, for example, so you typically have some motion blur on the facade of the building on the right side, while on the left side, or on the right side, you don't have this issue. So the image is much crisper, is much better. So these are implementations which are very relevant. We really, until 2 years ago, we never thought about this type of implementation of event-based technology. Because we were very much focusing on sensing type of application. We didn't think about imaging, but this actually turns out to be extremely interesting for surveillance, IoT, some mobile application, action cam, etc. And then some other implementation which are more in the industrial automation world. So vibration measurement is one of these. So this is actually very interesting because each single pixel becomes a vibration measurement point. So we can measure vibration frequency and amplitude. And this is actually extremely relevant for predictive maintenance because changes in vibration is a typical indication of a failure mode. So this can be done in real time. It's the first actual implementation of a real-time tool for predictive maintenance using vibrations. And then particle size monitoring. This is relevant in an application of pharmaceutical and food and beverage. We are able to count more than 500,000 pixels per second at 99% precision with very nice actually performance of tracking because we are more robust against occlusion due to the natural motion segmentation of the scene. So that's actually very, very nice, for example, also for some jet monitoring applications, semiconductor industry. So we have a couple of customers now designing our technology in their machines, and they will actually go to market next year. Spatter monitoring, we are in the world of metalworking machine tools. For example, for metalworking using lasers. What is relevant here is that event-based sensor can detect and track high-speed spatters, which are generated by the laser when they do welding process on metal, for example. And this can be used, this information of the spatter pattern can be used to actually do some real-time quality control on the laser welding. So this is actually quite unique as an application because you need both speed, a very wide dynamic range, etc. And just one more is in the smart access control. Here we benefit from the fact of having a low data rate and sparse information to reduce computational cost and power of the system. So we are now, our customer in Japan is now embedding our actually detection tracking pipeline into an embedded platform to be delivered to the market before end of the year. So yeah, so until now it has been a fantastic journey with Prophecy, and we will keep growing and pushing and making sure the event-based technology will become a reality. Because the two things, I strongly believe that a technology and a technology invention can actually become a real innovation when it's combined by fantastic research as the one you have been showing so far, together with actually industry that is funding this research, is finding actually clear customer opportunity, because it is the way you can generate this virtuous circle of research and commercial exploitation. So today, Prophecy is a group of about 100 engineers or more. We are based in Paris. We have now presence actually in US, in China, in Silicon Valley, in Japan. And yeah, we see this, we have been assisting to a very growing ecosystem of partners that are now adopting the technology, and that's glad. I'm glad to do that. And yeah, so I think with that I'm done. So thank you for your attention. So if you have questions, I'm here with Davide, and happy to take any question you may have.
I think we're gonna take all the questions at the end, like we did with all the previous sessions.
Thank you.
All right. So next, we have a talk by Oliver. Let me make sure that this is Oliver next.
Yes, indeed. The next one is Oliver.
Yes, great. Okay.
But I'm not so sure that he's around.
Oliver, are you there?
Perhaps we can move on with Soshun, and then if Oliver comes back, we can swap places.
All right. Let me hold on. Let me introduce you first, Susan. So Susan Chen is the founder of CellPixel and one of the main producers of event-based cameras. He held a postdoc research fellowship at HK UST. He was a postdoc at Yale, and in July 2009, he joined the Nanyang Technological University as a faculty. CellPixel technology is now part of Will Semiconductor. And he will talk about the most recent development of event-based sensors and associated applications. Susan, please go ahead.
Hi. Let me share my screen. Can you see my screen?
Yes.
Okay, good. Yeah, it's like 3 AM on my side. I a little bit sleepy, but let me try to talk as clear as possible. Yeah, I mentioned that we have been part of Will Semiconductor since May 2020. Yeah, I'm going to talk about the recent progress in event sensor and also algorithms. This table shows our new sensor. Basically, in 2018, we developed a 1 million sensor with using front side FSI process. Each pixel is 9.8 by 9.8. And then this year, we are going to launch a new one with 2 million pixels. So you may wonder why, sorry, how come? It's mainly driven by some customers. They really wanted to have a higher resolution. So this one is mainly designed for application like in smart home and surveillance. It's used 3D process, 65 nanometer. Each pixel is 5.6 by 5.6. The readout speed is faster, so we can guarantee 200 mega events per second. But of course, we know that there are some special cases. For example, there could be a case that the whole row pixels, the fire together. In this kind of scenario, we use some encoding techniques. We can group them and using a very compact the amount of data and to represent the whole row. In this case, using the same amount of bandwidth, we can achieve equivalent of like 1 giga event per second of readout bandwidth. Also, you know, in the previous workshop, I have been introducing a time step method. We call it in-pixel time step. I'm going to mention this again in the following slides. But in this sensor, I mean, this 2 million sensor is because the application is mainly for smart home. So we don't need a very high accuracy of temporal resolution. So that's why we only build off-pixel time step. But in this sensor, we build some new features. For example, we have event rate controller. So basically, we can real-time detect the event rate, and then using this to control power manager, and then we change the clock speed to achieve low power consumption. This is the architecture of the new sensor. I mainly want you to highlight that since our previous generation, we have been offering MIPI interface. The main purpose is to connect the sensor directly to some mobile processors. So we know that in order to reduce the cost and then make the system smaller, we don't use FPGA. So in order to remove FPGA, so we must connect the sensor directly to the processor. So the only way to do that is using a standard interface. So that is MIPI. But MIPI has been traditionally designed for frame-based sensor. So basically, we have to do some changes. The way to do that, we have to pack the events into some pseudo frames. So in order to let the MIPI to recognize it and then process, so send it to the receiver. But this means this also means that at the receiver side, you have to decode the data. So this will give a little bit of kind of overhead in processing, but that's not much. I mean, the good news that is not much competition. Okay. This is the general architecture of our Pixel. We introduced is detailed in previous workshop. Here, just make a quick recap. It includes, the log photo detector. Then after that, after this called amplifier filter, the changes will be compared to two comparators. So either one of them is flipped, then there the event generated. The event will be memorized by the in-pixel memory. Basically, it's like a latch. So here we have an event, but at the same time, so we have another branch. So the event will be used to control a sample on hold switch. So we can sample hold two types of signals. One signal is directly from the log photo detector. So this means that when you read the event, you not only have the event position, the time step, but also can have its log intensity. So we believe that this will be useful for signal processing. So because the polarity will not enough to fully describe the property of the pixel at this moment, but if you have its direct intensity, so basically you don't have to guess, its intensity at the moment. The second information we can sample hold is the we call it in-pixel time step. Here I would like to highlight. So in the past 2 years, we found that some applications require very high accuracy of time step. So this can only be done using this in-pixel time step techniques. So let me talk about this in detail. So we know that many times we think the event sensor is idle. It's something like this. So whenever you, the changes is larger than some threshold, an event is generated. And we also think that it will be processed immediately. But in fact, it's not really true. Okay. The problem is that in the real sensor, many times, for example, if I put my hand close to the camera, so if you move your hand, you will generate a lot of events at the same time. So this will, the number of events will congest the readout bandwidth. So it means that it will generate latency. So the latency not only generated by the readout, but also is in fact related to the log photo detector. So the real sensor model is something like this. Wherever you have an event, wherever the light changes reaches to some threshold, an event is generated, but that doesn't mean that it will process at the same time. So it will be processed later. The interval between the two basically is the delay. And after that, the pixel got selected. But then we know that there is another delay. It's called the refractory time. So, so there are two types of delay, right? One is due to readout. You have many pixels there. Another one is refractory delay. So usually the second part, the refractory delay, we know that is programmable. So it's almost the same across all the pixels, but the readout delay is random. In the previous a few talk about the arbiters. So in fact, the arbiter is one problem. Okay. So the real model is something like this. I have mentioned. Let me use a metaphor to talk about this again. So if you assume that you have two objects, one is the blue hand, and another one is the red hand. Okay, the red hand happens, sometime after the blue one. So if you assume that the two motions happens, there is enough time gap between the two, using whatever kind of time step method, so we can distinguish them. We finish reading the blue one, then you read the red one. But if the two motions happening too close in time, then it's possible that the events will basically mixed together. Then you don't know who read out first, who should read out later. Okay, usually we know that the off-pixel time step is assigned when you select the events. Okay, but previously we mentioned the in-pixel time step. The in-pixel time step is basically when the events are generated, we assign its time step. Then later we read it out, but this will be, regardless its readout sequence. We can trace it back. Okay, so the problem is that we know that either you use Arbiter or use here I also mentioned in previous talk that from our fourth generation sensor, we begin to replace the arbiters using scanners. So anyway, you will be selecting some rules when some motion happens. For example, when the red motion happens, the scanner is at this rule. Is at this rule, at the 40th rule. Then you have new motion happens. So the next rule you selected will be 50. Okay, so you're going to read out the 51, 52, 53, and 56 together. So the red motion and blue motion, basically the pixels read out together. So next, you're going to continue to read to finish the blue ones. After finish this, basically the scanner will go back and it will begin to process the 20 rules. So therefore you can look at, there are some pixels. So these 3 pixels, they basically experience a very high delay. So you think about the arbiters. So arbiters can have some random sequence. Either you use the earlier version, the greedy arbiters. The greedy arbiters, there are possibility that it will be stuck at some branches. So after we finish all of the events, then we'll jump to another branch. So for sure it will have problem. But even you use for so-called fair arbiters, but the readout sequence is random. You cannot guarantee that these 3 pixels will have some kind of certain amount of delay. So because it's random, you don't know basically how much is it. So it's possible that the delay can be some millisecond or even longer. Okay, so therefore we basically realize the problem. We have replaced it by sequential scanners. So the worst case delay will be the time you finish the whole round of scanning. This is the worst case delay. So if you make the readout fast enough, you can guarantee that the latency is less than some millisecond. Okay. Of course, there are some other ways to make it even faster. But anyway, this is the best accuracy we can achieve using off-pixel time step. We know that so far, we think the event sensor has a time resolution of some microsecond. But to me, I think this doesn't make sense. If you have a jitter of millisecond, then what's the meaning to have 1 microsecond resolution? Okay. So therefore, for some application, if you really need very high accuracy, for example, some 10th of microsecond accuracy, you have to use in-pixel time step. Okay. Also, in terms of algorithms, we have some progress. We developed a fully event-driven kind of HCI system, including the initializer, tracker, and also classifier. I don't want to go to too much detail. The main idea is that we have this kernel. It extracts information from the temporal local resolution regions instead of treating everything like a 3D geometry, extract from its geometric local regions. This is the main idea of the tracker, also initializer. We use event density to basically identify where the hand is, because the system we developed are mainly related to this like hand gesture recognition, using hand to control or play games. Okay, we also integrated into a TV system. Finally, we also developed a kind of attention assistant system. It can also be used, in the driver monitor system. So basically, evaluate how many times the eye blink. Here we use one CIS, also event sensor. The main benefit is that we achieve very low power consumption, because the CIS we only needed to run at like 5 FPS. Okay, so the main work is done by event sensor. Then we use the CIS as like auxiliary kind of assistance. Okay, that's all my talk. Thank you.
Thank you very much, Susun. We are going to keep all the questions for the end. Please feel free, and I even encourage you to post questions on the chat box.
Sure.
And if you don't want to forget them, Oliver, in the meantime, has joined. And so Oliver is associate professor in CS and ECE at Northwestern University. He is the director of the computational photography laboratory. He has funding from a lot of like industrial sponsorships. He has worked in many other like fields in optics and vision, including 3D nanotomography. He will talk today about both hardware and algorithm co-design with event sensors. Oliver, please go ahead.
Great. Thank you, Kostas. Okay, so I have more slides than I can go through, so I'm going to kind of blast through this. Main thing here I want to get across is that the work here primarily comes from Nathan Matsuda, who was my PhD student, is now at Facebook Research Labs, Winston Wang, who just graduated last year and is now at Apple, and then Henry Chop and Shrutarshi Banerjee, who are PhD students at Northwestern right now. Okay, so I work in computational imaging. A big key component to this is this idea that you can make your illumination and your camera optics programmable, and that you can use that to design a forward operator that tells you how the important parts of your scene X map to intensities that you measure at each pixel Y. And the key here is thinking about the whole system from end to end. So you're considering not just how the scene information that you're interested about encoding optically via illumination and sensor optics get mapped to digital numbers that get read out by your sensor, but also what is the algorithm that's going to be used to process those measurements that you make. And so this is the end-to-end. This is the high-level concept of hardware, software, co-design, and we have applied it all over the place, from everything from problems at the nanoscopic scale. So Kostas mentioned these problems of nanotomography, but also at the microscopic scale, working on computational microscopy, as well as things at the larger scale, including some of the event sensing work that I'll talk about today, as well as things that are even larger at remote sensing and astronomical scale. Here's just one quick example. This is an example of looking around the corner where we use a very special source of laser, use it to image light that goes through a scattering medium. The actual measurements that you get made look like total garbage, but when you perform the appropriate computational algorithm that is aware of the type of illumination that you used, you can actually reconstruct scene data in a latent way from what otherwise would look like total garbage. So this is a very sort of canonical example of hardware software co-design. We picked a very special type of illumination to work with the type of sensor that we have, such that with the appropriate algorithm, we can reconstruct the information that we care about. So, and this is a slide from Emma Alexander, which I think really brings home why this is relevant to the event sensing community. And so a key idea behind computational imaging is this idea that we're not going to just treat each of these components independently. We're not going to consider the optics and the computation and the scene information to be completely independent. We're going to try to link them together. And you know, one of the great things that Emma talks about is this idea that this is something that happens in nature all the time, that intrinsically vision systems that occur biologically are linked to the type of computation that that biological system has, and that this is, at the end of the day, linked to some sort of biological imperatives like getting food or finding mates. So this is not a new concept. This is an important concept in nature, and this is partly why we are interested in event sensing, because we see it as a biologically inspired sensing mechanism that we want to incorporate into this computational imaging paradigm. And I'll just talk really briefly. I have no idea where I am in time, so I'm just going to keep going and just shut me off as soon as I've gone over. There's two things that I wanted to talk about. One is 3D sensing, 3D cameras, and the other is high-speed video sensing. And the first thing I'll talk about is this idea of 3D sensing. And so there's many different types of 3D sensing. I'm not talking about time-of-flight techniques here. I'm talking about triangulation-based techniques, specifically about structured light techniques. And so this is this idea of motion contrast 3D. And the idea is pretty darn simple. It's really just that you have this, laser projector that's projecting a point in the scene, that's moving across your scene, that is getting imaged onto a motion contrast camera, that is seeing the one point in the scene that that laser projector is reflecting off of. That is scanned really fast, and you get a set of readout from your event sensor that tells you which pixel fired at which location. You use that to tell you information about the disparity in the scene that you couple together with your laser projector timing. And from that, and from a calibration system, you can extract 3D information at very, very high speeds. And so this is the key here, is that for the MC3D system, we can scan across all of the pixels in our volume in the same amount of time that it takes to scan only a single point or a scan line of points from one frame, from a conventional frame-based camera. And so as a result, we can essentially reconstruct all the 3D information using this triangulation principle in just a single, the same amount of time it would take to capture a single frame from a conventional frame-based camera. But the real advantage actually comes from something else, which is this light rejection capability and the differential sensing aspect of event sensors or motion contrast sensors. So this is an example which is actually a structured light 3D scanning system where there's a laser here that's projecting light onto this light bulb. And when the laser projects light, we just get a very small change in the irradiance at that single point on the light bulb, which is then detected by the event sensor because there's a change in brightness there. And miraculously, this event system is not being completely confounded by the constant brightness, the biased brightness of the light source, and it's able to just detect the change in brightness due to the light source of the laser scanning across the surface. And here you can see a 3D scan of this light bulb being performed in real time. And so what this means is that you can do 3D scanning outdoors in very bright light conditions. Here's an example as bright as we can get. Nathan is outdoors using his 3D scanning system and comparing it side by side with a time of flight Connect-2-based 3D sensor, and we see we get pretty good 3D results, actually a little bit better than the better light rejection, ambient light rejection than the Connect-2 sensor. Okay, so that was 3D sensing. Just really quick about our high-speed video work. So the idea here is that we have a lot of background doing compressed sensing video. So we've built systems to capture spatiotemporal compressed video. We've also built 3D microscopy systems to try to capture 3D information of biological samples in real time. And all of this got us interested in using event sensors to be able to record higher speed video. And so one of the things that we played around with early on was this fusion problem where suppose that we have low frame rate, frame-based intensity video, and then we also have events. Can we figure out good algorithms for trying to recover video from that? at higher speed than the intensity frame rate at speeds closer to what you can get with the event sensor. And I'm going to skip over the results there, but I'll show some results that build off this, which was the same idea of trying to do fusion between intensity and events using this guided event filtering, which was one of the core PhD contributions from Winston Wang, who again graduated recently and is now at Apple. And the idea here is to try to perform motion compensation and extract gradients from intensity images and use those to guide the type of filtering that you perform on event frames that are generated from event cubes, event volumes. And so the first concept is this idea that if you have a texture in the scene that's moving at constant velocity, it produces event volumes that are where the intensity information is sheared. And so you have to have some notion of projecting the event volume before you compress it to an event frame. And you can use essentially motion compensation techniques to try to find which projection will produce the best motion compensation and maximize the contrast in the event volume. That's the first concept. So first you take a normal event frame and you don't process it the normal way. You try to use contrast maximization to get a better compression that compensates for the motion. And then the idea is that you take intensity gradients from an intensity frame and use those to propagate in a guided sense to produce better filtered event frame output than you would have gotten otherwise. And it works really well. So here's the event frames that you get out of what would otherwise be an event frame being processed at low resolution. So you get higher resolution, higher fidelity, better edges, better fidelity to the intensity gradients that you are capturing at the same time. And it's useful for all sorts of things. So here's an example of an event tracking algorithm that completely fails when you're looking at native event output, whereas if you're using guided event filtering, you could produce much more robust tracking from the event frames that are produced using this technique. Okay, I wanted to talk about this a little bit. I didn't have a chance to talk about it in my slides. I just really briefly, here is a architecture where we have come up with where we're trying to solve this rate distortion problem. We assume we have a chip that can capture both intensity information and events, and we're interested in understanding how much information should be sent via raw intensity and how much information should be sent via raw events. And there's a lot inside of this. You can look back to my slides if you're interested in this topic. We have a series of publications on this. One of the core components is an edge reconstruction algorithm that takes in events and a distorted intensity frame and uses it to produce an enhanced frame. Here's some examples of a distorted frame. So this is highly pixelated, so highly compressed. Here are the events that are sent. We also have mechanisms for producing event compression. And the idea is that these two things together produce something that has much higher fidelity intensity output and can be fed through a object detection or tracking algorithm on a host chip that has limited bandwidth with a sensor. And these are the kind of interesting things that you can do with this is you can look at these trade-offs between the ratio of amount of bits that you're using to assign to your events versus the amount of information that you're assigning to the intensity information and find out where you get a peak performance with respect to a specific track. So this is an example of tracking a car in the Need for Speed data set. Okay, so with that, I'll just say that the latest thing that we're interested in looking in is SNNs and specifically looking at hybrid analog and spiking-based neural networks, and we have some interesting results in that was just published at ISIP. And with that, I'm sure I've gone way over, but thank you for humoring me and letting me do that.
No, that's what was actually very good in time, 10 minutes.
Oh, it was? Okay, so I made it.
So we will proceed with the last talk. All the questions will be at the end. And the last talk is by Sony AVS. The speaker is Christian Brendley. Sorry, I'm navigating across too many windows here. So Christian did his PhD at ETH with Toby. And after he graduated, he co-founded the startup Insightness. Insightness was acquired by Sony in 2019. And now Christian is the CEO of Sony Advanced Visual Sensing. Christian, please go ahead.
Thank you very much. Thank you very much for this kind introduction. And thank you also for the possibility to present here at the homecoming day of event-based vision sensing. So it's really nice to see kind of all of the faces again. I mean, unfortunately, I don't see everybody, but at least see them listed. And so, yeah, you have these slides also available with me kind of stuttering over them. And so if you want to go a bit deeper in there, please do so. So I'm going to just quickly kind of give a very, very short kind of fly through. Sony, it's a name that you may have heard of with really excellent headphones. I really like these ones. And I'm pushing forward the name here a bit because having been a startup CEO, I know that research and development often kind of forgets where the money is coming from. And we're very thankful for kind of having such a great mother company. And with that, I thought, actually, I'd also like to give out some more shout outs at that point. First off to my team. They were the ones that actually made all of this possible. Then secondly, the people that got us here, the investors that believed in Insightness. And then before that, all of the people at I&I. I think many of us wouldn't be in the field without I&I. And more importantly, big shout out to Toby. I think the majority of us in here would not work on this topic without Toby. So I think this is a great opportunity to say thank you. And then to the sponsors, I think we should all be aware that public taxpayers are paying for a lot of this. And so I think Switzerland has really great taxpayers. So please come to Switzerland or at least bring your money here to the bank accounts that we have. We also have great bank accounts here. And so then last but not least, thank you very much to all of the organizers. So to Guillermo, Davide, Costas, Cornelia, and then Davide and Prophecy for sponsoring. So I quickly wanted to use this rather than kind of reiterating what is already said in this super strange recording. I really do not like the online format. So I like to have the audience around to see whether people actually like what I'm saying. But yeah, you can look a bit more into more details there. So yeah, Sony, we're doing semiconductor. We do this very successfully. Largest player in the market and with some of the most exciting technology. Now, I think this is one of the nicest privileges of being acquired by such a great company is kind of suddenly seeing behind the scenes, and it's just mind blowing. So it's really, really, really cool to see what is all in the pipeline and what's all happening here. So it's really nice privilege. And with that, I mean, that doesn't come from nowhere. And so there's a whole range of research entities across the world. And so we're one of them. Sony AVS is one of them. And as mentioned before, we're here in Zurich or in Schlieren, more specifically. And we used to be called Insightness. We've been working on event-based vision sensors for very long. I would say, like me personally, for about a decade. And we've been doing all sorts of interesting things. You may have seen our YouTube videos where we sent one of our co-founders to drive in front of a drone. Or where we did like some inside out tracking. So we've been working a lot on, with this technology. And so I thought instead of just kind of giving only an overview of kind of some of the most recent results that I'm allowed to show, I thought I'd also like to share some of our insights, some of the insight I personally had across along the way. And I think, well, I tried to put them into formulas such that you can digest them also after the talk. So this is the first formula here. I think in similar forms have been around at many different times, but for me, it's an important one because it clearly distinguishes what we call event magnitude from the threshold. So the threshold is what triggers the event. The event magnitude is the amount of temporal contrast that you actually capture with an event. And I think this distinction is often not really properly made, and I think it should be done. It helped us a lot to kind of start figuring out, okay, what is actually signal and what is noise? And the signal is an integral of temporal contrast. Now, what is very important here, again, I mean, the motivation behind looking into all of this is because we tried to kind of build better sensors, and so we had to figure out what is important for the software people, and so we had to figure out how to properly kind of capture what they need. And so one dimension that we figured out, which makes it a bit nasty to define all of this, is that constant signal in most sensors is like a constant input. And for an event-based vision sensor, not so trivial, at least to me. A constant input is a constant rate. It's a constant increase in light intensity. So if you want to characterize SNR, good luck, because you look at a moving signal when you just roll it out in time. And so that made it very tricky. So we did some more digging. I think we have now some new nice kind of tricks on how we can do this. And I think that was the second insight. So first, distinguishing between event magnitude and the threshold, and then secondly, figuring out that that it's the SNR has to capture two dimensions. It's not just the intensity and how accurate we can kind of represent the magnitude versus the threshold, but also how accurately we can actually capture the time. And then I think the last one is that usually we express the thresholds in terms of percentage, and that makes it a bit nasty because you then have an increase that is not the same amount in absolute percent. And so if you just use it as a factor, it's also interesting from a mathematical point of view. You can formulate things a bit easier. That at least were some things that helped me a lot in the past. And I think that was the formula that helps us a lot to think about the future. When we think of, okay, what makes up the event magnitude? So if we drop all of the noise and assume a perfect sensor, then an individual event, what does it capture? And unfortunately, it's a huge mix of things. And once you start kind of looking a bit into what this mix is made up of, you can see that, for instance, here, this is the optical flow equation. Nicely, it's in terms of reflectance. So I think that I did like once this derivation. It's very nice to see that you're kind of illumination independent directly in the math there. But what you can also see is you can see what are the problems that when you have a bag of events and you want to make an inference, you have kind of this under constraint problem. And so what you need to do is you somehow have to kind of properly correlate either along time, along X, along Y. And the other thing that we figured is nobody so far, at least that I've seen, is working on using events for reflectance change inference. Now you see a lot of inference around if you correlate like events along time, and you know what the external signal is, you can do active illumination, so you can do structured light and these funky things. And then if you do kind of correlation within space-time along X, Y, and T, then you can kind of do this like contrast maximizations and the like. And so I think that's kind of then helped us also to think about, okay, well, what can we actually use it for and where it may actually be suitable. And I think one dimension that is also very exciting here is like if you just use the event magnitude, it's a very nice entropy cue, and it helps you to kind of guide processing. Now, one reason I kind of would like to emphasize this is because what we have learned in the past is that the front end of an event-based vision sensor tends to be noisier than the front end of other sensing technologies. And so therefore, at times, it may be just helpful to use the events kind of as a guide rather than as the main information source. And I think like just a previous talk kind of nicely highlighted this, that it's an important trade-off to make kind of, so yeah. Then some examples. So yeah, again, if you know how your pattern looks in time, then you can nicely correlate your event stream against it. This gives you kind of really nice videos. As here, you can do this also very fast. Also nicely shown in the previous talk. So I think that's a very, very nice property. Then the very well-known tracking. So again, here. What we've been working a lot is making these sort of things more robust. It's not necessarily trivial. It's not what gets you the nice papers, but what is a very important task. And again, once you start doing these sort of things, you start to realize how important noise is and how important it is to kind of properly characterize it and then design your sensors accordingly. And then the last item, okay, here you can also see what the advantages are if you do this tracking. So yeah, even in the presence of motion blur, you can continuously track, or in the presence of kind of repetitive patterns that are self-similar. You don't have these kind of tracking issues that you have with, let's say, OpenCV with this Canada. Then, so the last one, I think that's also a topic mentioned in multiple discussions. I mean, we're not reinventing the wheel here. Is kind of just fusing different sensing modalities. Again, I mean, events have really nice properties. They have some strong shortcomings. And so if you can kind of combine the nice advantages of one sensing modality, such as a depth sensor, with the nice low latency and the low power consumption of the EVS, that's very useful. So yeah, this has been kind of a quick overlook of some of our activities internally. And so, yeah, we're always very happy to have more talent on board. We're soon going to kind of have some more positions open. So please follow us on LinkedIn. Then also check out some other exciting Sony jobs. Again, Sony's a pretty exciting company. It tends to be kind of, forgotten big when you look at the real big American or Chinese companies, but it has been around for some time, and it has aggregated some really, really exciting technologies and potential. And so, yeah, please also reach out to me if you're interested in a job in a really cool company. Thank you very much. I tried to keep it short. We already lost about 10% of the audience in this session already. Now we're down to 50 people, so we're even lost more. So yeah, I tried to keep it short. Thank you very much.
Thank you very much, Christian. I love the formula that you showed, and we start with this with a question from Kobina. Kobina says it's the right way to look at it, and all these variables though are confounded, and to unconfound them you need the ground truth, like the gradient of R.
Yeah, I'm just saying this is what's really going on, and this is how you should communicate it to your team, what the sensor is doing.
So I think for us, it was very helpful to kind of realize that a single event doesn't give you anything. And actually 2 events even don't give you anything. And then only once you have a bunch of events, you can start aggregating them into some sort of inference. So as soon as you throw in some additional constraints, as I know what is like the external signal you want to correlate it to, then you start getting to some interesting points. Now, the real challenge, and again, this is why I talked a lot about noise, the real challenge then comes to question how many events do you need to aggregate until you get a reliable inference? And that's very much a question of noise. And as you start digging deeper there, you start realizing, again, this noise is more than just like how well your sensor captures a step. It's very much a function of how well it can encode a slope. And it was a bit tricky to think about this, and at least for me to wrap my head around it, but
and the slope
it helped us a lot.
yeah, and Christian, the slope changes the latency of the analog part. So that's also changed.
Yes.
You need yeah. So yeah. but I'm just saying, unless you write these things down this way, the application guys and the software guys, they totally don't understand. This is a language that they can understand. So that's what you need to do.
Yeah, and even more so, you have to come up with metrics that the software guys know, hey, look, this is a sensor that actually works for my application. And that sensor may not be so suited because at the end of the day, I mean, Sony Semiconductor, we want to sell semiconductors to the people that develop algorithms and to develop software. So yeah, that's where a lot of the thinking comes from.
All right, there is one question for Oliver about the extreme examples for lighting conditions in the 3D reconstruction and in terms of extreme range, which was answered in the chat box. I would like to ask Oliver, in the projection of the laser, which exactly property from the event-based sensors is used? Do you use the exact timestamps of the sensor, for example? Are you synchronizing somehow the laser projection with them?
It was basically, so there's a temporal calibration between the starting phase of the projector, which is periodically scanning, and there's a sync signal basically coming from the projector. So we actually used a pico projector. Actually, we had multiple systems. So one was a Galvo-based laser scanner, which was the outdoor system, which used a homebrew laser scanning system with an infrared laser, and another one was using just a pico projector with a MEMS-based scanning mirror. And in both cases, we had a sync signal for the projectors that we were using to perform temporal calibration with the events coming out. And that's really about it. So basically, based on the known scanning position as a function of time relative to the sync signal of the laser scanner and what the events timestamps were coming out of the event sensor, the difference between those basically told us what the disparity was. And that's as far as we did. So we didn't do, there wasn't any smart denoising. And in fact, all the stuff that Christian's talking about understanding the noise in the event sensor and how it actually affects your ability to be able to do inference was not some, I would say we only scratched the surface of that. And there's still, I'm sure you guys have looked at some smarter ways to process the data that you get from a 3D sensor like that.
Other questions, feel free just to unmute yourself and ask.
I have a question, Christian. Do you use the features that you said that you're tracking, and we've seen lots of corner tracking today in the workshop. It's good to have them and to be able to, detect them and track them, but are we using these corners or these features to do visual odometry?
So I can't go too deep in depth on what we actually kind of do with this. Now, the part that I can talk about is that we use this often kind of to assess also the quality, and because it's a thing where we can get easily kind of to grant with. It's something when you just track something, it's very nice because you can run a lot of experiments because you exactly know, okay, what are you actually looking for, much more than when you don't know the underlying let's say dx dt and dy dt, which you know very nicely in a lot of these cases. When it comes to let's say SLAM visual inertial odometry, I think at least I would say from what I see kind of out there, it appears as if the IMU starts to become the dominant sensor, and then you take vision from time to time to kind of correct for it, at least in some of the let's say commercial solutions out there. So still not fully clear to me whether EVS have a strong differentiating edge for just the VIO or SLAM part. There are definitely corner cases that you can probably only do with EVS, but the commercial impact of these ones is hard to assess.
I can add something about this probably because at the end we are collaborating also with Sony, so we have some experiment also with feature tracking. The problem with the feature is that Chiara said before in the talk, when you increase the resolution, everything slows down because you are doing a process 7 by event, and this is affecting also the performances. Often all the literature is based on the dataset provided by Zurich. It is done on a QVGA resolution, so it's very challenging already go to VGA and megapixel. So we observed in Prophecy that you can extract feature. There are features that you can use for to optimize the localization. And with Sony now, currently there are some development for this also.
So I have a question for David and Luca, and thank you very much for showing all these applications. It's really very motivating how to talk to the other people outside the field. Do you find that the HDR, I have seen for the cabin application is mainly HDR, right? It is not really speed or. Do you see the applications involving just the HDR aspect of the events being actually pretty critical?
I don't know, Luca, what you want to answer or I go?
Yeah, go for it, David.
So, okay, in HDR, there are a lot of nice work. There was a presentation done by also by Robert at the beginning, but also the 3D work, the work done by the group of Zurich, the group of Scaramuzzo, so Daniel. They are doing fusion with frames, and they're trying to recover the high dynamic range from the events. So they are correcting the frame images, collecting information with events, fusing together to find the detail that usually are lost in the image. And this is very interesting. And we are having also, we have a both situation, only events and fusion with frames. Of course, it depends a lot by the use case. Another example is the arc welding. Before in the presentation, Luca was presenting this pattern monitoring. Usually with the arc welding, you have the problem to find the point of soldering and track this point of soldering and do the close the loop to control. And this is an application that currently is a product. It's not anymore a research project. It's a product that will go on in production very soon in partnership with a big company. And this is a full HDR. In automotive, we have a long experience. We have a lot of example of HDR in the data set of DSEC of David. There is a lot of example of HDR, especially in changeable illumination, tunnel, and so on. And this is another classical situation where the HDR is very important. And of course, the driver monitoring system. Currently, they are using infrared light for the commercial application, but in this collaboration with Xperi did the full development of the algorithm. We just supported from the point of view of the software, and they're ready with the product. Now they're proposing this solution as a product between their portfolio. So this is quite amazing, and it's very promising. And I can say that the HD camera improved a lot this, especially the quality of the HDR.
Mm-hmm. Other questions? There is a lot of praise about Christian's formula, and definitely this is what I'm going to go and present to my students tomorrow and discuss it. Guillermo, do you want to take back over?
Sure. I think if there are no more questions, we could start wrapping up. Mm-hmm. So I would ask you to turn on the cameras and take a screenshot, if you don't mind. I mean, thank you very much to everyone who is here to the end. There are about 50 participants or so. Thank you, Shoshun.
We had also a lot of people like Shoshun in China. I'm
yes,
very sorry.
May I make a little advertisement? Sure. In a week from now, so starting June 28th, the Tellerite workshop will start 1 week, every day about 2 hours. Registration is for free. Please enjoy. You hear more about spiking computing and event-based processing and others.
Yeah. And if you were not able to attend any of the talks today, the speakers made a fantastic job pre-recording the videos, and they are available online. There is a YouTube playlist, and the slides are also available. So thank you very much. Thanks very much to everyone who contributed to the workshop with the papers, the reviewers, the co-organizers, the speakers, and the sponsor. Let me take a screenshot. Okay, another one, because this one only half of it worked. Seems to be working, yeah. Okay, well, I think that's it. Thank you very much. Have a good day.
We need
Thank you. Bye. Thank you very much. Bye.
Oh, nice seeing you.
Thanks, everyone.